Hello, ma'am. Good morning. Am I audible to you?
Yes, sir, audible.
Romania, ma'am. Good morning.
Good morning, sir.
Good morning, Romania Concheva, ma'am. Am I audible?
Yes, sir, you're audible.
Yes, I hear you.
Thank you, ma'am.
Hello.
So very soon the program will start. So it will take some time.
Ashish sir, good morning.
Sir, good morning.
I think first talk will be the Chandan sir, na?
Yes, sir. Yes, sir.
Okay. Romania madam, good morning.
Good morning.
Thank you for joining with us.
Thank you too for the invitation.
Great. Oh.
Hello, Dr. Pradhan. Are you there?
Yes, sir. Good morning, sir.
Good morning. So we can start, right?
Yes, yes, sir. Yes. Ranjita, madam,
Sir, yes, I'm there, sir.
you can start. You can start.
Okay, okay. Thank you, sir. Thank you, sir. Thank you.
Research is something that you don't know but are willing to find out. The galaxy of intellectuals, Your Excellency, invited delegates, esteemed faculties, and all enthusiastic students. A very warm good morning to one and all present here. I, Vishnupriya Mishra, feel fortunate to get a chance to interact with you all. And a very warm welcome on behalf of the Department of ECE, GIT University, who has organized and arranged a platform for all of us in this international conference on smart and sustainable technologies 2021. In this conference, we are going to get a vast knowledge and ideas on current smart technologies which is ruling the world and will rule the world in future. This is the right time for the youth to take the advantage of this session and get new ideas to develop themselves and thereby contributing themselves in the developing the nation. I truly hope this session too will going to be a inspirational and motivational one for all our young minds. Ladies and gentlemen, ladies and gentlemen, allow me to introduce you all to an academician for whom continuing with an research is not easy, it's really worthy. He is not such a scholar is Dr. Chandan B. Samantrai sir, who is currently working as a professor in the Department of Engineering at the Virginia State University, USA. Currently, his research focus is stochastic memristor circuits, memristor-based physical unclonable function, and true random number generators for both hardware and cybersecurity publications. Also, he has other active research area in neuromorphic computing devices. He has several years of past research experience in the field of modern VLSI devices and emerging semiconductor memory, including DRAM, NVRAM, RAM, and CMOSFET. So, without any further delay, let's grab some knowledge from Chandan sir. Sir, please.
Thank you, everybody. Dr. Pradhan, you can hear me and you can see my slides, right?
Yes, sir. Yes, sir.
And stop me if you cannot hear or cannot see. So let's start. Welcome everybody. Of course, the young mind, as she said, thanks her to nice introduction. And let us go ahead and learn some, new technology. I did a lot of, modern VLSI, microelectronics, CMOS. Those are electronics computer engineering. And we are doing some neuromorphic computing, that is your brain-like computing or device. Now, all of the idea, all of the research we apply to smart and sustainable technology, which is very important for us. And one of them is called packaging. Now, you do not know how many packets you are using it every day. You don't remember that. But how it is made, who is making that? So one of my, key research is your smart or intelligent packagings, right? So what happens like intelligent packaging is made by definitely through your electronics, computer engineering, computer science, right? So let's go forward. Now, what is the outline? Outline of all packaging system, IoT sensing, Internet of Things, quality assurance, NX design, 3D printing, and conclusion. Now, when you graduate, all the students, when you graduate and go to a company, you will definitely face the quality assurance. That is very important before the product goes to your customers. So it is a supply chain. It is a, it is a ergonomy, I will explain, logistic, marketing, of course, and sustainability and safety. Now, while we are discussing this, the package, let us discuss a very simple thing. Every day we are doing eating 2 times, 3 times, outside, inside. Definitely we need a packet or a container. How safety, how sustainable, and ergonomy, not economy, is ergonomy. Ergonomy is how we can build that. Different types, huge and $1 million industry of ergonomy. For example, when you soft drinks, I'll come to now. So, for example, like, packaging, when you take soft drinks, how it is made, what's the design, how it becomes cooler, either liquid soft drinks or milk. So there are different types of packaging, primary packaging, secondary packaging. What is that? What is primary? Primary does mean when you contact to directly to the container, liquid, most of the liquid. Coffee, Starbucks, okay? So secondary and tertiary is all the company product. And as a whole, you can load it, unit load, and then it go to industry, packagings. So packaging is huge, not only food. You can think of how microchip is packaged, semiconductor industry. how to your computer package, when you buy a computer, laptop, how it comes to your home. So there are a lot of learning point from packaging, right? Now, therefore, it is an emerging market. How we can build smart IoT sensors in order to, the smartphone-based food diagnostics, how you can check the food is whether it's correct, incorrect, whether you can buy or don't buy. Do not neglect food market is $1 billion market, 1,000 crore market, the food market, vegetables market. Okay, now modern way, when you go superstores to buy fruits, vegetables, they are all, most of them organic and high-tech foods. Definitely there is a price gap between outside and inside. Now, so therefore, lab on smart biosensor, smart spectroscopy, it depends on the, there is a filter, and there is LED, and there is a camera, a CMOS image camera, right? And it is Wi-Fi module. And, sometimes you can, we can algorithm like machine learning and deep learning to control the small sensors. So you basically need most of IoT and a cloud computing idea to build this. Okay, you definitely need science background, but you need more engineering background. So you need a Arduino, those are working computer engineering students, Bluetooth, and a chip, spectrometer chip, microchip, LED, filter, light switch. Try to build it in your school, in college. You are making project smart IoT sensor. Make it cheaper. Try to make startup. Try to make it is your incumbent in your college, and try to sell to local farmers, local fishermen, local all type of people. Sometimes give them free how they are using, whether you can predict food quality. You can sometimes you can think of weather, think of soil, think of different types of crops. Very small background, and it is a huge market. Everything science, engineering, technology, then market. You have to buy, you have to sell. Now, similarly, when you put a spectrometer on chip, everything on chip now, system on chip, biochip, and a semiconductor chip. So you need Android operating system, smartphone, and there's a microcontroller, right? And then you can modulate the signal and control the signal, IoT platform or cloud. That means, for example, you will have a large farmhouse and you have a lot of organic, which is very costly. And then you are driving, you are flying from Bhubaneswar to New Delhi or Bombay, Mumbai, and when you get there, by cell phone, how you know how much your product is good or bad, kind of thing. That's you need, cloud, you need Wi-Fi, you need, how everything will be integrated. It's not easy though. I did a couple of my computer engineering students, but it's not easy to do very simple things. Sometimes we have some nanotechnology platform, which is easier to visualize, but difficult to achieve. nanotechnology is very easier. If you listen the name, you can think, oh, okay, it is nanoscience. Therefore, it is very easier. We have idea that science is easier, right? But not. So when you come to nanoscience, measurement is very important. So quality control, package, intelligent package, right? With your, RFID tags, everything when you make a package to measure nano sensor effect is very tough. But we need the nano sensor, which is a modern form of IoT nano sensor, to control all the food supply chain. Why? One story like that, in whole over the world, on the planet Earth, we spoil food, maybe 25%, 30% food we don't eat and throw it, right? Why? Different reason, right? Quality food, cooking quality is not good, or you bought a old stuff, old food, or you bought it something wrong, whatever. Now the idea is, you can refrigerator, right? Refrigerator, you can put the food, you can keep 15 days, 20 days, 1 month, right? How you can keep the food for several years. So when we can build smart refrigerators, and it can, or something new technology, then food scarcity, hungry, and everything. So this idea, this presentation I'm giving, that is a part of world hungry. How you can eradicate hungry, how you can hunger, right? A lot of we are putting a lot of money to other countries, kind of things. How? So that the technology is the idea. Now, intelligent packaging. You are buying everyday package, but not intelligent package. For intelligent package, which can give you temperature and gas, freshness, everything through RFID tag. Now, the RFID tag can be fed to your cell phone, and you can get everything in your smartphone. You can get everything in Apple Watch or iPhone. So smart. Yesterday I told everything smart, right? The smart device is your cell phone, smartphone, and everything. We are making smart doors, smart windows, smart refrigerator, eventually smart homes. You can put money on smart real estate, right? Now, smart intelligent packagings. There are different new terms. When you join a company, you will find this ergonomic packaging. What is that? How the package is made. It's not like you can make by hand. They're putting crore rupees ergonomy. Like a bottle, how it is made. There is a design principle, it's called ergonomics, right? Informative packaging, information technology you need. Active packaging, right? And so everything is controlled by RFID. It's pretty common, and barcode. When you go superstore, you are getting barcode. So IoT, cloud, and your Wi-Fi modules, RFID, sensors, everything combined make or build intelligent packaging. Now you can believe, now scientists are developing. We are also working paper electronics. Same paper, the paper will print a lot of sensors, lot of IoT nano sensors, and that paper you can try. That paper will print, and it will be sold. You can wrap your food. Okay, now McDonald's will give you with that wrap. So you can find how much calorie. You don't need the smartphone. You can automatically scan the barcode to your smartphone. Then you can get calorie and it's hot or cold and whatever you need. That is coming in a part of supply chain. That is coming a part of business. Everything end in business, making money. So that's the goal idea, how to build the intelligent packaging. Therefore, you need RFID antenna, how the antenna works, RFID reader, and the data coming, going, and there's a transponders. Now the transponder is coming like car when you're driving, easy pass and a speedy check, everything by transponder. So RFID tags serves as a passive and active detectors. Everything it will detect, right? The temperature, a food package, product name, whether you can eat or not eat, how long you can keep it. So that is a supply chain from farm to fork, farming from the farmhouse to your fork, farming your dinner table, right? Farm to fork. So building the internet of things with Bluetooth. So what happens, we did Arduino, and we have exactly like the other sensors, and my students build some of the from scratch. So they build some temperature sensor, pressure sensor, humidity sensors. That's very important, and all will combine to Wi-Fi or in cloud to control the device. They need Arduino IDE, Arduino RFID tags, and humidity, temperature sensors, LED, etc. And they build that. That's successful, but now we have IoT sensors for food packaging testings. So IoT sensors you can see that is your conductivity, thermistor, temperature, pressure, humidity, oxygens. You can think of in a COVID time, COVID-19 and Omicron, you can think of how to make pressure, oxygen sensors. You can build through IoT nanosensor, convert to oxygen sensors. It's a part of the technology. So now, therefore, what happens packaging and ergonomics? What is that? Now, ergonomics you see here, when you open a bottle, like medicine bottle or food packet, so you rotate, right? You rotate anti-clockwise. It's very easy, you think. But when the company made it, there's some principle. It's called ergonomics. Packaging ergonomics. Now, the question is, for example, a patient in hospital. So he's old, okay? How he or she will open it? How minimal? So the opening the medicines, tablets, pills. So that's the ergonomy. That I gave one example. So this is a huge market, $1 million market, crore rupee market, that ergonomics in packaging designing. It's designed be hazard free, safeguard, all hazards all type of, not only medicines, all types of pesticides, bottles, and all types perfume bottles, food or liquid soft drinks, everything is depends on packaging ergonomics. So do not, we daily for example, someone tell you the business. So when the business come to your mind, young mind, you think of what? Okay, I will make a software company. I will make artificial intelligence. I can do social media, Facebook, Insta, and kind of LinkedIn, Twitter kind of things. You never think one thing like water bottle. Now, water bottle, drinking water business is 60 billion US dollar. Is very close to the price or shame to Facebook. It's very close to Google, believe me. Drinks like water, how to get water. So when you think of a water business, huge, something new in water, definitely you will hire chemist people, then you will hire mechanical engineer people, then you hire ergonomist, how to design a bottle. And then you'll hire, computer engineers, electronics engineers. Why? They will put Wi-Fi, IoT, all things will come. That's the company. You can build a company, but the major important thing is water quality. What type of water you are selling, right? But eventually you need this type of people to run your company, right? So you should know that how to start a business out of your school. When you go out of your college, then how to make a job or a business startup. Then you can learn from these presentations. So packaging, design, and simulations. So you have to definitely hire someone to design and modeling simulation software, IT people. So they will do now CAD, 3D modeling. There you have affordable NX design or any other software. Then see when then water or soft drinks, right? Pepsi, Coke, and they're inside a bottle. What happens? There is a stress level, right? They're all time inside the bottle. So how to manage the stress level? So therefore, the bottle design, bottle weight, capacity. So don't think it's small thing. It is a huge business. It is a huge startup. You can immediately start up. Then how to print the bottles with the labels. Labels is your barcode. From the barcode, you can scan by smartphone. You can scan the labels and a lot of things, right? That what happens after when you barcode. All the information comes, right? That's why you need some IT people. They will do modeling. They will do barcode, set Wi-Fi, IoT, all the compactification on the compactified bottle design and kind of things. After that, after all these things, you will go to the manufacturing process. You can do at this age, I'm talking special students, all students are hearing here, you can do everything. You can do a company, you can do manufacturing. At this age, if you start, after 10 years, you will be a huge manufacturer of any type of, Therefore, you need 3D printing. 3D printing is the 3D printing. Now, 3D model, you already got last slide. There is a code, and then 3D printer, you have to buy series of 3D printers, like your, is like copy, Xerox, copy. Then you have to like 3D Xerox, 3D printer. It can created by 3D model. We discussed. Software depends on the how much you are paying for software. Export the model, G code, and then 3D printings kind of things. So your bottle can come up as a 3D printer product. So you see, now we did some 3D printing work, NX model and 3D printing. My students did. These are all 3D printing products, either short or tall or like short designs and the 3D printings with some bottle, and we did any simulation of pressure and temperature stability, how the bottle can sustains. So like a coffee, like a Coke, like all types of liquid drinks, and also food packets, also other packets, not only food, like huge, you can think of, make a list how many. So we did the simulations, and then quality assurance. When you join a company, the last stage is quality assurance. What is that? That is your business. That is your marketing. If your quality is good, everybody buy it. That's quality assurance. Now, you see one bottle is called biodegradable polymer, right? Now, after drinking this water, you throw it. What happens, you see? Several hours, it automatically melt down, degrade, and merge to our atmospheres. So IoT enable applications of sensor, food packaging, and control the quality. And RFID nanosensors also, help to product quality. Now, your cloud computing, through cloud, you can, you can check authentication, tracking, locating, product features, all things. And you see, all has, you have to hire the people of IoT people, cloud people, RFID engineers when you make a company. And this is under research. You cannot get this is under research. So that is very, very important, and bio-friendly, eco-friendly, right? That's the thing. That's the talk, like how we develop the smart packaging, how intelligently we made a packet, how IoT-based nanosensor can track the quality assurance, and how the design and simulation helps. What is 3D printing? And by how we make a startup, increment, company. Why not company? And I gave the idea, like you can start a water bottle, and water bottle business is I'm telling, like world the largest water bottle is your is kind of like believe me, it's the price is close to like 60 billion US dollars. Don't neglect that. Forget other drinks. Water is very important. So that's a very simple talk about all types of smart technology, how you can make your startup business along with your study. Once after your study done, you can jump to entrepreneurship and think of your idea. And this technology nowadays is very, very much available. You can do at any time. So don't depend on others. You can do a job, that's okay, but you can do yourself. So that's the tech-friendly, user-friendly talk. That's why it's all dedicated to students. So you have to, carefully, everything you can do, and yeah, that's it. This talk. So you can have, if you have any questions, you can ask me. Is nothing traditional talk. So you can ask any type of, I can give idea of startups, increments, R&D, research and development, right? So, and of course, your dream should be fulfilled, right? Along with the study. So everything not book. You have to do some outside your book or laptop. You have to try something new. That's it. Okay, thank you everybody listening the talk. Dr. Pradhan, over to you. And yeah, if you have any question, you can ask me.
Thank you, sir. Thank you for giving us knowledge about packaging and for motivating our students to develop smart IoT sensors which can help the farmers to grow healthy food. And thanks for giving some startup ideas.
Now, I can add one thing like this is, of course, the food starting from very simple idea, water, food, whatever. But remember, everything comes as a package. Your cell phone, when you buy a cell phone, is come as a package, right? When you microchip package, so 1,000 article, 1,000, instruments, everything on package. So this is the learning point. How the packaging industry is a huge industry, and it's like semiconductor or steel or petrochem industry. Package is a huge industry. So, yeah, go ahead.
Thank you, sir. Dear participants and attendees, I'm profusely elated to introduce our guest of honor, Dr. Romina Koncheva, ma'am. Ma'am has completed her MSc in Computer Science in 1973 from Technical University of Sofia, Bulgaria, and did her PhD in 1977. She joined as a senior researcher TIE in 1992. Presently, Dr. Koncheva ma'am is working as the Vice President of TK Engineering, Sofia. Her main scientific interests are image processing, image compression, and digital watermarking, image tensor representation, CNCs, programmable controllers. Her total number of publications include 176 journal papers, 18 book chapters. She has delivered plenary speeches at international scientific conferences and scientific events. Also, she has handled about 45 scientific research
We cannot
projects.
hear.
Yeah.
Dr.
Thank
Pradhan,
you.
we cannot hear. Yeah.
With immense respect and honor, I warmly welcome Romina ma'am to throw some light on the smart and sustainable technologies for future. Ma'am, please.
Thank you, Sanan sir.
Yeah. So we are done. Dr. Pradhan, are you done?
Thank
Do you have any questions?
I think no question from the student side. Thank you, sir. We'll be in touch.
Okay. Okay. Thank you, everybody.
Hello.
Welcome, madam.
Okay.
We can start.
Can I start now?
Yes, ma'am. We can start. Just wait. Okay, you can start. Welcome, sir. Roman sir.
Okay, so I shall start. I shall share my screen now with the presentation.
Great, sir.
Do you see it? Do you see it? Do you see my presentation?
No, madam.
Can you see it now?
No, madam.
No? Very strange.
Yeah, hello, madam. Actually, directly you go to present now button.
Do you see your slide now?
Yes. Yeah. We got, sir. Now
Okay.
you can just make it full screen, madam.
I'm afraid when I am working in full screen, I change the slides from here, but they don't change at your side.
Hello, madam. Hello.
Hello?
Please, madam, make it full screen, madam. Slideshow. Make it slideshow.
Yes, I understand. Is it okay now? Do you hear me?
Yeah, madam. Start slideshow from beginning. Just like first.
Yes, I press the slideshow, but
From
I
the
don't
beginning,
see.
there is another option. Is there at the from beginning? Is there?
Yes.
Yes.
I'm not sure if in this mode my slide will be really changed. So is the slide changed now?
No, madam. It is not displaying over here. The changing.
Yes, this is why I avoid showing full screen.
Okay.
When I transfer to full screen, I change here the slides, but you do not see them. So
Okay,
I shall
madam. No issue. You can continue.
work as it is now.
Okay, madam. You can proceed like this way. Otherwise.
Okay, thank you. So, dear colleagues, I shall present our research, which is about multidimensional image representation based on pyramidal decompositions. And here it will involve from the beginning how it was started with orthogonal transforms up to deep neural networks. The outlines in brief. So first we start with state of art, then the basics, the spectral image pyramid. After that, cognitive neural network pyramid for 3D objects model. And after that, some more specific versions of this approach. So, what is the contemporary situation in this area? First, the digital image representation basically has the primary forms, which are matrices and tensors, and secondary forms, which are the Gaussian Laplacian pyramid, multi-resolution pyramids, spectral image pyramids, pyramidal structures used for two-dimensional object recognition based on neural networks, feature pyramid network, adaptive and multiplicative pyramid net, convolutional neural image pyramid, and Laplacian pyramid based on generative adversarial networks. First was the Laplacian Gaussian pyramid, which idea is that when we take the initial image, it is left down corner. Then after decimation and followed by interpolation and subtraction of these versions, we get the image which is shown in the down right side. After that, we do similar operations up to the higher part of this picture, and we get the Laplacian pyramid, which permits to show the same image with very small number of coefficients, and this way to enhance the transfer and the compression and so on. So this was the first attempt for such approach. You see that we start with large number of coefficients, which corresponds to the big picture down there. And we finished with small number of coefficients, decomposition coefficients, which is the top of the pyramid. So we have a regular pyramid with wide basement and narrow top. The main derivatives of the Laplacian pyramid are reduced sum difference pyramid, S-transform pyramid, and so on. All these pyramids require to calculate the coefficients to use multiple two-dimensional image filtration, subdiscretization, and interpolation. In the result of these operations, in the restored image, appear many various distortions of the kind aliasing. And also, all these pyramids have high computational complexity because the operations which must be performed are relatively mathematically difficult. The next structure, which was already based on neural networks, is this investigated by Cantoni et al. So here we have the initial image transformed through tensors, and then we use, after some training, we get the next level, which has a smaller number of tensors, and we proceed to the top of the pyramid, and in the right part are shown the interlayer and intralayer connectivity of the processors which perform the calculation of the tensors. This is the structure of the pyramid for two-dimensional object recognition based on neural networks. Then another structure is the pyramidal neural network PyraNet. Here the architecture is comprising two kinds of layers. The first are the pyramidal layers, which are shown here, and then one-dimensional feed-forward layers, which are data sequences. So in this network, nonlinear two-dimensional neurons are trained to perform image feature extraction and dimensionality reduction. The next basic pyramid is feature pyramid network based on Gaussian Laplacian pyramid. Here it is also bottom-up oriented. This is first the Gaussian pyramid, then the Laplacian, and here is shown the lateral connection between the layers. The next pyramid, pyramidal convolutional network. Here also the pyramid is oriented as it is usually known, with a wide basement and a small top. In the beginning, we have a basement of input feature maps, which is a database. Then we perform the training and the learning procedures, and after that we get the output feature maps. Additive and multiplicative pyramid net. These are two structures. The left is the additive, and in the middle is shown the multiplicative pyramid net. So the difference here is that in the additive pyramid net, the feature map dimension increases in linear, following linear relation, while in the multiplicative version, it increases geometrically. And here are shown the residual units in the pyramid. Different convolution operations are performed there. Convolutional neural pyramid based on Laplacian pyramid. Also here we start with the input data. The pyramid is positioned here. convolution blocks are shown here. So this structure permits to enlarge the processed field without sacrificing computational efficiency. And Laplacian generative adversarial networks for image representation. This is a pyramid of 3 levels, which uses 4 generative models to sample an image of size 64 by 64 pixels. The generative models are train-tuning using the conditional generative adversarial network at each of the levels. So this is shown in this block diagram. And UNet with scale pyramid module. This is quite new research, it is on the deep learning approach based. So we have a training image. After that, we convert it to grayscale. Then follows the training, and the scale pyramid is shown here. Now we go to our approach, which is the spectral image pyramid, and which is called inverse difference pyramid. In fact, it is inverse because we start with small number of coefficients, and after that, in each consecutive level, the number of coefficients which are calculated is increasing. But unlike other pyramids, we can stop the processing and transfer at any moment when we achieve the quality of the restored image which we need. So here there are two kinds of such pyramids. The first are statistical, which use the Karunen law of transform, PCA, SVD, and deterministic, which use digital Fourier transform, DCT, Walsh-Damar transform, and so on. So all these pyramids do not need multiple sub-discretization and interpolation, and in the restored image, they are avoided the distortions of the kind aliasing. And also the computational complexity is very low compared to other to the pyramids which were shown before. And besides, we can use various kinds of fast algorithm for calculation of the Fourier transform coefficients, Walsh-Damar transform coefficients, and so on. So we have two kinds of pyramids: adaptive inverse difference pyramid with DNN and cognitive pyramid neural network. Image representation based on adaptive inverse difference pyramid with deep neural networks is called AEDP-DNN, and the cognitive pyramid based on adaptive spectral pyramid decomposition with neural network control is CPNN. So in these approaches, we use the human way for image recognition when we start with some small similarity. After that, we increase the similarity to get the final image with high quality. The inverse difference pyramid, here is shown the mathematical representation. This is the input image matrix for two-dimensional image, BEG. Then we, after the transform, get B0. And this is the difference between the approximation, which is B0, and the initial original image. It will be explained better with this block diagram. So here is the input. B is the input original image. For this example, we used the image block of size 16 by 16 pixels. It is processed by some kind of orthogonal transform, and we calculate the transform coefficients. So if we use only 4 coefficients in this first level, we save them for further processing. After that, we execute inverse orthogonal transform, and is obtained in result the restored image of naturally a very low quality, because we use only 4 coefficients. We subtract it from the original one and get the difference. In fact, it is called the error between the approximation and the original. So this error we divide into 4 pieces, and for each of them we also calculate the next set of coefficients, which are obtained here in this S1 to 1, 2, 3, 4. In this level, we get for this image block 16 coefficients. But if we continue this way to the next level and to the end of the decomposition, the pyramid will be over-complete. This means that instead of the initial number of coefficients, which correspond to the pixel of the original image, we shall have much larger number of coefficients after the transform. So, in fact, we shall expand the representation of the image. To avoid this, we use some mathematical relations which exist between the 2 levels of the transform coefficients. And when we already have the lower level of coefficients, we don't need to calculate all these coefficients in the next level. So for the second level, instead of 16 coefficients, we have to calculate only 12. And in the next level, instead of 256, we can calculate only 240 coefficients. And in this way, the pyramid is not over-complete anymore. And also, we can, in each level, introduce the function f0, f1, and so on, depending on the level of the decomposition. And we can reduce the number of coefficients which we use. In this way, we get a non-over-complete pyramid. Here is shown the reconstruction if we use 4 coefficients only in each level. So in the first level, here it is shown for the whole image processed at once. So if we use 4 coefficients only in the first level, we get only gray level. In the second level is obtained this. This is when we use DCT transform, because for Walsh-Hadamard, for example, we would have squares just of different grayscale value, and here is shown, you can see the change of the cosine functions in each of these parts of the image. So we start with the initial level, which is P0, and at the last level, which is P8, we get the restored image, which is the same quality as the original. This is for image of size 256 by 256. This is why we need 8 levels of the decomposition. This pyramid can be also created by adding a neural network in each of the levels, and this is why it is called adaptive two-dimensional inverse different pyramid with two-layer backpropagation neural network. So in each of the levels, we put there in the part where we calculate the coefficients, a backpropagation neural network in which, after training, we set the weights of each of the coefficients, and after that, the number of the coefficients is reduced significantly because in result of the training, the values of some coefficients are very small. This means that they equal to zero almost, so we can neglect them. And here, this is the left part is the coder and the right part is decoder. So in the decoder, we perform our operations in inverse order to restore the image. As I mentioned before, we don't process the whole image at once. We initially divide the image into smaller pieces, for example, 16 by 16 pixels, and we scan the image in this way, usually in this way, because it is called meander scan, because in this way we get higher correlation between neighboring blocks. Anyway, some other kinds of scan are also possible. And here is shown the block diagram of the autoencoder. And here are the mathematical relations between the input vector of m on square degree, on 2 degree components, the vector h, and so on. Here are shown some of the results obtained for two-dimensional adaptive pyramid. You see the famous image Lina. In the first level, after compression 1 to 128, which is very high compression ratio, we get the PSNR of 35 dB. In the next level, only 2 levels are used. The PSNR is already 37 dB and compression is 1 to 64. And similar results are got for the image which are also shown here. Naturally, such processing is, so it is compared to JPEG 2K. Naturally, our processing in this way is a little slower than JPEG, but the results are very good. Here are shown also some comparison results for JPEG 2000 for different images. The next version of the pyramid is cognitive neural network pyramid for 3D object model representation. Here, our approach is used for image retrieval in image databases. For this, first, the images in the database are all transformed in our way, so they are saved in the database as groups of calculated coefficients. And this, we are looking for the relation between these coefficients values and the coefficients which are calculated for the queried image. So here is the input. The processing starts with the lowest layer. The features are extracted and we get some kind of model. Then this model is evaluated if it is good enough, and it is good enough for this layer, for this initial state. We continue to the next layer with the next set of coefficients, and this way we are going to the higher levels of the decomposition. In fact, usually it is not necessary to make many calculations and approximations with too many layers, because after 2 or 3 layers, in fact, the object is recognized. Here is just shown a set of images. This is the original set. Then in the first layer, we get these approximations, and in the layer 2, the coefficients are gathered together, which we have for these 2 layers. The approximations which are obtained are here. If we continue with one more level, the approximations are already very accurate, so they are good enough to recognize. In fact, in this way, in this case, for the recognition, is not necessary to receive very high quality of the image. It just similarity is enough. Block diagram of the system for image retrieval by content based on 3-dimensional cognitive object model. So this is, here is the query image input from the left side. And then we start again with the initial level, and here is shown the same approach again. 3-dimensional inverse different pyramid for 3-dimensional tensor image decomposition. So here we already work not with 2-dimensional image, but with 3-dimensional tensor representation, because this is suitable for multispectral images which have high similarity between them, or for sequences of images such as the images got from computer tomography, or also for video sequences. In all cases, when we have a high similarity between the group, some groups of images. So here is the tensor block of 8 by 8 by 8. Here we perform 3-dimensional truncated orthogonal transform and get the coefficients. And then we divide the tensor into smaller parts and perform the similar operation. This is the coding part, and in the right side is the decoding part. So this is non-recursive decomposition, and when we have recursive decomposition, we perform first all the calculations here. And after that, when the calculations for all levels are finished, we transfer them to the output. Comparison of the computational complexity for 3-dimensional inverse difference pyramid based on Walsh-Damar and 3-dimensional discrete wavelet transform. It is based on the number of additions and multiplications. So in our case, it is here, the first line. The number of coefficients is only big for the additions, but multiplications are a very small number. So in fact, the number of needed calculations is much lower than any other than the 3-dimensional discrete wavelet transform. Here also is shown a graphic representation of this research. So our case is the blue. So we have high number of coefficients only for the last number of levels, but usually we stop the processing in the lower levels. But it is only additions which are performed very quickly. It's easy to add digits. While here the number of multiplications is significantly low for our case. It is here, the blue case. While the red is for the discrete wavelet transform, it is shown here, it is constant and the scale is different. This is while in the right side we have different scale. It is for discrete wavelet transform. For fast Fourier transform is the green line, and for SDT is the yellow line. So in all cases, our approach has much lower computational complexity. The advantages of the tensor decomposition based on the reduced inverse difference pyramid are that we get high concentration of tensor energy in a very small number of spectrum coefficients, which are placed in the initial level. So this permits us to reduce the number of needed coefficients. Then minimum computational complexity compared to other similar approaches. And the future development will be to investigate various 3D decomposition to extend the n-dimensional pyramid for a sequence of tensor. This is tensor train. And also to be developed algorithm for compression and high and multi-level search in a tensor DB. So now, the composition of 3D tensor of size m by n. So this is, for example, a tensor which will represent a sequence of computer tomography images. Here is shown in the left down graphic the distribution of the energy in the coefficients. So you see that the initial several coefficients is concentrated almost all energy at the image. After that is approximately 0, and at the right lower part is shown the tensor representation of Walsh-Hadamard function. This is three-dimensional Walsh-Hadamard functions, the initial ones with lower frequency. This is the application of three-dimensional IDP for content-based multi-level search in a tensor DB. So here is the representation of the tensors in the DB, and this is the input query tensor at the lower left part. So we introduce here the coefficients and compare them with the coefficients in each level. So in the first level, if there is no similarity, we reduce the search, we stop the search because, for example, it is the query image is not from this group of images, and go to the next group. So this enhances the process very much. Three-dimensional inverse difference pyramid based on deep autoencoder. So in this case, it is the same pyramid, but we already have here deep learning introduced because the neural network which is used is multi-layer, and in this way, in result of the many hidden layers which are into this neural network, we get very small number of coefficients which are after the training, which are needed for the representation. And as a result of this, the compression is really very good. But naturally, you know that in deep learning, it depends on the training. So the main advantages of the presented architectures are, first, that they permit high image redundancy reduction, in the result of which is obtained minimum description, and the image quality is restored. Also, energy concentration, which we get, is very high in a small number of decomposition components. So this permits its use to various applications. Then image data mining in large databases turns to a new approach, in fact. Also, the computational complexity is relatively low. And we can achieve automatic tuning for the model's parameters because of the because we evaluate the quality of the image, the restored image in each of the levels. And also we can create models which involve learning with deep neural networks, in result of which we get high flexibility and easy tuning. Here are some of our related papers, because this is a long-year research, and we continue now the research in our new projects in the frame of the Technical University of Sofia. And we hope that we shall have more results soon. So thank you for your attention. I hope you are not too tired.
Sorry, ma'am. Audience, do you have any questions?
Yeah, finished. If there are questions, yes.
Okay, ma'am. I think no one has any questions. And thank you, ma'am. Thank you for explaining us about Gaussian Laplacian pyramid, pyramid, and pyramid convolution, feature pyramid networks, very clearly using different block diagrams and images. And you explained us and you gave us an idea to how to reduce the image redundancy even by keeping the image quality as it is. Thank you so much, ma'am.
Yeah, thank you too.
Thanks to Roman madam, Roman sir also. Thank you, sir. We'll be in touch. Hope that next year conference you will be with us, because we are going to continue this series. Okay, and we are planning to do in the month of December. If possible, kindly visit in the offline mode.
Okay, thank you very much. We shall be happy.
We will wait for you people. So definitely we will discuss with you and we will plan accordingly so that you will be with us physically.
Okay. Thank you very much.
Thank you, sir and madam.
Thank you, ma'am. Now, one of the great personality with high experience in industrial, research and academic domains is Dr. Arnanshu Mahapatra sir. Dr. Arnanshu Mahapatra sir is affiliated with Electronics and Telecommunication Engineering at Veer Surendra Sai University of Technology, at Burla.
Breves. Sono sono chiamati.
He is currently providing services as Associate Professor. He has authored and co-authored multiple peer-reviewed scientific papers in publishing houses of international repute like IEEE, Elsevier, IET, Springer, etc. He has presented works at many national and international conferences. His contributions have acclaimed recognition from honorable subject experts around the world. He is actively associated with different societies and academies. He is a senior member of IEEE. His academic career is decorated with several reputed awards and funding. He has more than 20 years of industrial research and academic experience. Presently, his research team is working on research areas like localization of sensor nodes in indoor and outdoor environments, fault diagnosis in wireless sensor networks, outlier detection in sensor networks, spectrum sensing, and allocation and 5G networks. So, hereby, I request Arnanshu sir to please proceed with his intellectual thoughts.
Yeah, am I audible?
Yes, sir.
Yeah. Thank you very much for the introduction. The screen is visible to all?
Yes, sir. Yes, sir.
Okay. Thank
Yes,
you.
sir.
Thank you. So I was listening to the previous lectures very carefully, and hope most of you are enjoying that. First, before that, I should say good morning to all. Today I will try to present something about some of my works that we are doing here, and that is fault diagnosis in wireless sensor network. One of my PhD scholar is doing on this topic. So before moving towards what are the techniques that involves in this fault diagnosis, let us have a look about the fundamentals of wireless sensor network very quickly. So we can say that is when we are talking about wireless networks, means the wireless network can be categorized into two different broad categories. Like one is infrastructure based wireless network, and second one is infrastructure less wireless network. So for the example of infrastructure based wireless network, if you will say that there is some existing infrastructure present. So in that infrastructure, we are having a base station already that is placed by some service provider. That means a well-defined architecture is in its existence. And if any user want to enroll him or herself in that network, then directly he or she can come and request a service provider. The service provider will allow them, they can join the network. That is the infrastructure based network, where a base station and some predefined infrastructure exists. So I'm not going in detail of how it happens and all these things, but to have a simple knowledge. So in other way, another network that exists, that is called as your infrastructure less network, where we don't have any base station, or otherwise we can say that if we want to make some network on demand. Example, I can say that yes, all of a sudden if we do require to manage some disaster, and if the technology can help us to face that particular disaster, maybe it's maybe a tsunami, it may be a cyclone, or it may be any kind of disaster which is unpredictable always. So if to tackle with those kind of disasters, if you want a network, that means it is on demand. So for a particular time we do require that network, and beyond that time we may or may not require that network. In that case, with no time, we are not in a position to have an architecture that this infrastructure based network is having. So to cope up with this situation, we should think about some other kind of network, and that is called as your infrastructure less network. So in this infrastructure less network, the popular networks that we are having today is your mobile ad hoc network, and another is your wireless sensor network. So when I will talk about this wireless sensor network, which is nothing but the foundation stone of Internet of Things. So now Internet of Things, or IoT popularly we are calling it, is a buzzword in recent era of technology, and people are talking much about this IoT and doing research much in this area also. So where this wireless sensor network is the foundation stone, that is the foundation above which this total IoT is getting built. So here in wireless sensor network, we can say that in our real world situation or real life situation, sensors are everywhere. In our day-to-day life, we are encountering so many sensors. While we are using air conditioners, we are having sensors. In refrigerator, we are having sensors. In washing machines, we are having sensors. In dishwashers, we are having sensors. In micro oven, we are having sensors. In our mobile phones, we are having sensors. That means, though we are not aware of all these sensors, but still those sensors are working for us. Now, since we are having an enormous number of sensors, a huge number of sensors distributed throughout the globe, now it is our prime objective should be how to organize those sensors and how to create a network of all those sensors, so that the information from all these can come to us, right? And how to store them and how to index them and how to use them by using a network is the biggest challenge of the sensor environment. Right? Before that, there was a myth, that is in early or late 90s. What are the assumption? That only thousands of homogeneous sensors that can be used, and there should be a mesh network where the sensors are placed in every corner of the mesh cell. But in practice, now it has been found out that, and everybody realizes that now the sensors are not thousands, but it's thousands of thousands of thousands. We cannot imagine how much sensors are there in the globe. It is a very huge figure. Since it is a very huge figure, so the amount of information they are gathering and they are generating is also very large. So the processing of these informations is also a challenging job. So based on that, there are very diversified fields of research on wireless sensor network, and it is having different type of challenges. So as I told you, the IoT is nothing but the buzzword today, and a huge research and market potential of IoT is there. That's why the wireless sensor network is playing a major role in this field of research. So before that, to understand how this fault diagnosis will work, let's understand the sensor. So the first thing is we need to sense something. That should be a transducer which converts one form of energy to another form of energy. So once it senses some information, it may be a temperature sensor, it may be a humidity sensor, it may be a image sensor, it may be a CCTV sensor. So many type of sensors are there. It may be a ECG sensor, that is in the body area network. So the sensor is sensing some information, and after sensing, since we know that the sensed information is in analog form, and we require to process the information in digital domain, so we need to convert it into digital domain, right? And all these things to be operated by battery. So a battery source should be connected, and after this signal is converted to digital domain, then we are having some digital signal processing, and we do require some amount of memory to either store and to store the algorithms and what are the requirements, some informations that need memory. And once it is signal processed, then we are having a transceiver which makes the modulation, encoding, decoding, demodulation, all these things is doing. And once it has been done, the signal is getting transmitted from the sensor node. So this is a typical diagram of the sensor node, which senses the information and transmits those information. It is not doing anything else. So on other way also we can see some other presentation of this sensor node may be like this. You can see that is one thing more here I have put, that is it's called as power management. In most of the applications of this sensor node or sensor network, the sensor nodes are deployed in human inaccessible areas. Most of the applications, I can say 90% of the applications of wireless sensor networks where sensor nodes are deployed in human inaccessible areas. So since it is deployed in human inaccessible areas, so definitely those sensor nodes should be battery operated. Since those systems or those nodes are getting battery operated, so the prime objective of any protocol designer is that how much less power it is utilized to sense the information and sending the information and doing other job of the sensor node. So for that, the power management plays a major role, where it follows the rule of your sleep and awake. That means if or it can be a type of event driven. If an event occurs, then the sensor node is getting awake, and once the event is over, then it can go to the sleep stage to conserve its energy, battery energy. So some of the operating systems that I told you, that is there, you can say that these are all most of our your free operating systems. This is to give you some of the examples of those who want to do research in this area. So these are some operating systems and some simulators. There are several simulators are there. So I have only cited a very few. These are all open source simulators. So we need not to pay for them. And some licensed simulators are also there, but it is always advisable to go for your open source, because why I am advising, I also do advise to my students that if we will go for open source, then we can contribute to that particular simulator also. So we are using Castellane. So to understand the wireless sensor network, let's start with an example. So while deploying a sensor node, first we do require an internet already that is existing and a gateway node. The gateway node is nothing but the node which connects the sensor network to the real world. The real world I refer here is nothing but the internet. So you can see, excuse me, a node is deployed. First, a node is deployed. Once the node is deployed, then they will do their job automatically. Because as I told you, the sensor nodes are generally deployed in human inaccessible areas. So sometimes the sensors may be dropped from air. There are several ways of deployment of the sensors. I will give an example in this lecture or in this talk, that how to deploy by using a automated vehicle, that we will see with a case study, right? And once, or I can say that the sensor nodes should be self-organized. Once they are deployed, then what it is doing, it is trying to find out which nodes or which entities are in its proximity. Proximity means in its transmission range. So if it finds something in its proximity, it will try to get its identification number and will create a neighbor table and will put that identification number in that neighbor table and will consider that that particular entity is its immediate neighbor or one hop neighbor. So here, once this node is deployed, you can see the gateway node is nothing but it's in its proximity. So it will create a link to the gateway node. Similarly, two more nodes I deployed, then they will do the same job. They will do searching for the neighbors. Once they find out that yes, they are the neighbors, then they will create a link. Similarly, more sensors are deployed. They will do the same job and they are creating a network. Now you see, if something is coming in between, some barrier, communication barrier, though these two sensors are nearby, so since the communication barrier is there, it will not create a link. And this will also communication, due to the communication barrier, there is no link. Now the sensor field is created. We have deployed all the sensor nodes and we are clearly saying that this is a sensor field. So this, let's say for example, this sensor network, what we have designed is to sense the rain, happening of rain in some geographical area. So we can see that yes, rain has happened here, and those sensors deployed in that area will sense the information and they will send the information to the gateway node. The gateway node is directly connected into the real world. Now this happens. You can see now the information is now communicated to the gateway node by using a routing algorithm. I am not going to in details of the routing algorithm here. So it will find a path, shortest path to reach the destination, and it is not a single hop communication, rather it is a multi-hop communication. So from the transmitter, that means from the source to destination, now we are having number of intermediate nodes. Since we do have number of intermediate nodes, we will call it as multi-hop communication. So in either you go for sensor network or mobile ad hoc network, or in general, if it is a infrastructure-less network, then we will go for your multi-hop communication. Let's say, for example, you see in that case, due to something, this node is failed. Now, automatically, the network will find a different path. You can see earlier, this was the path. Now, this node has failed. This node has failed due to some fault or due to some misbehaving node. The misbehaving node means it may be misbehaved due to some fault or due to maybe some external attack, that is security threat. So if this is not working, so what will happen? As I told you, the network is self-configurable and network is intelligent, so it will follow another path. You can see this path is now followed up. This path is now followed. Now, as I told you, it's a multi-hop routing. Now, deployment, as I told you, deployment of sensor nodes. And earlier, that is, as I told you, in the late 90s, the myth was that people are talking about whenever the sensor network is coming, it will be a mesh network. But it is not a mesh network, rather it is most of the application, it is the sensor nodes are deployed randomly. Sensor nodes are deployed randomly. So once the sensor nodes are deployed, means a sensor node will have a sensing range and the sensor node will have a communication range. The sensing range means the area in its proximity, how much area it can sense. That is the sensing range. Similarly, the communication range means what is the maximum distance it can communicate. That means the information can send or information can be received. So based on that, different models has been suggested. This is the basic model, disk sensing model, which is not generally used. What we can see, that is the coverage of the sensor node, it will be equals to 1 if the distance between the point P and the sensor node SI is less than the sensing range. Then it will be 1. Otherwise it is 0. It is that much of easy. It's very fundamental. But usually it is not utilized because due to the presence of some obstacles in and around of the sensor node, we cannot say that it will be always a disk structure. Rather, it may have some contours. So to go for that, to cope up with this, we should go for a probabilistic model. So the probabilistic model as suggested here, you can see I am not going in details of it. So this equation you can see it is having different alpha and beta. Here we can say that it is having some alpha and beta, right? So based on this lambda and beta, we can plot a graph and the graph may looks like this. So this probabilistic model says that what is the probability that, or I can say it is the confidence level. Other way we can say that it is confidence level. What is the confidence level? The confidence level means how much confident the sensor node is that it can sense the information to a particular distance. So where this lambda and beta measures the detection probability. Detection probability means it is the, if a objective is there at a particular distance, then what is the probability that the object will be detected or sensed? And it has been defined by these two parameters, lambda and beta. And by varying different value of lambda and beta, we can have different detection probability. And it has been observed that up to a particular distance, the probability remains almost 100%. And beyond some distance, the probability falls for different lambda and beta, and it is having different structural fall. So this is how to deploy. And as I told you, we'll be discussing an example of how to deploy the sensor nodes. And it's a very interesting example. It has been published in 2010 that it is by using an unmanned aerial vehicle. So they are using image processing here to deploy sensor nodes in an area. How they are going through? So the autonomous deployment sensor nodes, that is that vehicle UAV, is moved to the location. Then they are taking that vehicle is taking the grayscale image of the terrain. Then it is making the segmentation using some image processing techniques. And after making the segmentation, it can find out the points by using some thresholds where to deploy the sensors and where not to deploy the sensors. And based on that, it is taking finding whether this terrain is of interest where the sensor needs to be deployed. If yes, then it is deploying, or otherwise it is not deployed. So it can be well understood by observing this diagram. It is the area of interest or terrain where the sensor nodes need to be deployed. We can see these green areas are now the water levels or water bodies. Now other areas are also, that means the area of interest where the sensor nodes need to be deployed. So obviously the sensor nodes should not fall in the water body. And the sensor nodes also should not fall on some rocks so that it will get destroyed. So what the technique they have suggested? They have suggested they are taking the image, grayscale image, and they are making it segmented. Once the things are getting segmented, then they can find out that yes, this area is the water body. We should not put those sensors in those water bodies. And at the end, we can see the sensor nodes are not deployed in the water bodies, rather those are deployed in the area of interest. From this deployment strategy, we can say that we are not following in mesh structure that was the myth in earlier 90s. Rather, the sensor nodes are deployed randomly. Sometimes they follow certain distribution, and sometimes they may or may not follow some distributions also. So this is one of the example I have cited over here, how the sensor nodes are getting deployed. There are several ways of deploying sensors in the sensor network. One of the example will get surprised to know that putting sensors in a rocket, and they are just bursting the rocket so that the sensor nodes will be deployed in a particular area. Now, some of the examples I need to cite here: sensors in agriculture. But the thing is, what should be the cost of? One of my student is working on this area, that is to fabricate sensors generally used for the find out the health of the soil. That we are working on that is to find out the soil health. What is the salinity of the soil? What is the temperature of the soil? What is the humidity of the soil? What is the micro and macro nutrient contents of the soil? That we need to find out. But as we approached the market, we found the sensor usually required to sense those parameters are too costly. The landing price for sensor, we are finding it is around $320 US dollars. So in that situation, we decided, since it is too costly, so let's go for or try to have a very cheap sensor, which may cost 5 rupees, 10 rupees, 20 rupees, 30 rupees. Let's say it's all and around 100 rupees will be costing one sensor. Since it is utilized in agriculture, so is taking the viewpoint of the farmers of Indian state. So the people cannot purchase if the sensors cost are more. So the solution may be some optical fiber sensors. So in this optical fiber sensors, what we are doing, you can see. So we are removing a part of the cladding. We are removing a part of the cladding, and after removing the part of the cladding, we are depositing some material which is sensitive to a particular parameter of the soil. For example, salinity. We'll choose some material so that cladding material will, when it will come in touch with the salinity of the soil, then its refractive index will get changed. I do repeat, when the cladding material comes in contact with the salinity of the soil, its refractive index gets changed. So when the refractive index gets changed, so the evanescent field structure will also get changed, and the amount of power absorbed in that fiber optic cable is also get changed. And at the receiver, we can see that this is a paper that we have already published. So the power meter is getting calibrated, and we can find out the particular strength of the particular nutrients of the soil. So these are some of the nanoparticles that we can have, that is to find out humidity, iron chloride, the ammonia, low molecular chemicals. These are some of the parameters that is having in the soil and all this, whatever it may be. So accordingly, these are the nanoparticles that we need to deposit on the cladding, and we can design sensors, low cost sensors that can help in the agriculture. So this is actually we have designed to find out the alcohol content in the water. This is an example. Okay. Now we'll switch to the actual topic of our interest, that is fault diagnosis. Now we have created a network. We have deployed a network depending on our requirement and all these things. As I told you that the sensor network is self-organized. Once it is deployed, means since these are deployed in most of the cases in human inaccessible areas. So since these are in human inaccessible areas, means and most of the times these are also deployed in hostile areas. That means there is a chance that the sensor nodes will be faulty. It may be due to the aging of the sensor network, maybe due to the age of the sensor network. Let's say after 1 year, 2 year, or 3 year, due to the age of the network, also fault may appear, or due to several reasons, the fault may appear. So since fault appears in that particular node or some of the nodes of a particular network, sometimes this fault may be catastrophic or life-threatening. For example, if we deploy network to find out the forest fire in a big forest, if somewhere in the fire or somewhere in the forest the fire is ignited, and a particular sensor node deployed nearby, if it is faulty and could not sense that fire, then even though we are network with us, the fire is not getting sensed in prior, so a corrective measure could not be taken care in time. So the objective of the network should be, the fault should be identified. Once the fault is identified, then every node in the sensor network must know that a particular node is faulty with this node identification number. So that is the objective of fault diagnosis in wireless sensor network. So we need to first detect the fault. That means we need to make a binary decision. Either a sensor node deviates from its normal behavior. Its normal behavior means it will sense the information, then it will process it, and it will send it. This is the prime fundamental behavior of every sensor node. Apart from the sensing and sending, it will also work like a relay node, because as I told you, the total network is now a multi-hop network, rather it is a single hop network. Some intermediate nodes are playing a major role to send information from the source to destination. So apart from the sensing its own information, sending it to the destination, it also does the duty is that of a relay node. So if a node deviates from its normal behavior, that needs to be detected, a binary decision should be taken. And to locate all faulty sensor nodes in a network is called as a fault diagnosis. And to estimate the severity of the type of the fault is called as the fault identification. So these are the three fundamental points every researcher has to be in their mind while talking about the fault diagnosis in a large. And what are the other terminologies? That is, one is correctness. The diagnosis is said to be correct if there are no fault-free sensor nodes mistakenly diagnosed as faulty. These are the performances measures that we need to calculate while we are trying to evaluate the performance of the protocol that we have designed. Next is completeness. The diagnosis is said to be complete if all faulty sensor nodes are correctly identified. What is consistency? All sensor nodes agree on the same set of faulty sensor nodes at the diagnostic route. That means there should have some consensus that yes, these are the group of sensor nodes, those are not behaving properly. And latency may be the time elapsed since the appearance of the fault to the isolation of the sensor node. That means once the sensor node is diagnosed as faulty, that need to be isolated from the network, keeping into mind about the K connectivity of the network. Another definition and terminologies may be your communication complexity. That is total number of diagnostic messages exchanged in the WSN to ensure correct and complete diagnosis. That means whenever you are trying to detect the fault, what we need to do, we need to send the test message to test something, we need to send a test message. So how many number of test messages we are sending? That means in the process of diagnosis, how much communication messages has been sent, or to satisfy the performance of your particular protocol. Is we know that the maximum battery energy utilized in transmitting and receiving of number of bits. So we should keep in mind that the communication complexity of any protocol in any network, whether it is infrastructure based network or infrastructure less network, the communication complexity should be less. It means the number of diagnostic messages exchanged must be less. And detection accuracy defines the ratio of the number of faulty sensor nodes detected to the actual number of faulty sensor nodes. If there are 10 number of faulty sensor nodes are there and I have detected 9 nodes as faulty, then my detection accuracy will be 90%. Similarly, false alarm rate, it is the ratio of number of fault-free sensor nodes diagnosed faulty to the actual number of fault-free sensor nodes. If I have diagnosed one fault-free sensor node is faulty out of 1000, then my false alarm rate will be 0.001. So your detection accuracies must be high, false alarm rate should be low, communication complexity must be low while you are designing a protocol to diagnose the faults in a sensor network. So what may be the sources of faults? Sensor node calibration may be a fault, hardware problems such as poor connection, software faults such as incorrect computation, your noise that we'll see, and residual energy. Residual energy, it means if the battery is getting depleted faster and the battery energy left is small, then the node may also misbehave. These are the source of the fault. So why we need the fault diagnosis to increase the network lifetime? So the definition of the network lifetime, that is worst case definition, I can say that a network will be dead if one of its node is faulty. It is the worst case definition I can say. Then your data delivery, if an intermediate node is faulty, as we have seen in our animation diagram, that if in between a node is intermediate node is faulty in the multi-hop communication, then the data delivery may be affected. Then judgment of accuracy in the sync node, if we are receiving faulty information from faulty nodes without diagnosing them as faulty, then the judgment accuracy of the sync node also differs from the actual. Then the network traffic. Network traffic, why we were saying that if we are allowing the data generated by the faulty nodes to propagate in the network, then unnecessarily we are just misutilizing the network traffic. So in wireless sensor network, that means what are the challenges we are going to face while designing the diagnosis protocols is first is the resource constraint, because the communication resource is less, the battery is getting operated, the signal processing resource is less because the sensor nodes are very tiny in nature and they are low cost. So definitely the resource constraint will be there, and they are randomly deployed, and there may be some dynamic network topology, and attenuation and signal loss these are the factors generally influencing the protocol design. Now, how to classify this fault? This is the classification that we have suggested, and in published it is in the IEEE Communication Software Tutorials. This is our classification. So we can see the fault can be broadly categorized into three types of faults. That is permanent fault, intermittent fault, and transient fault. Permanent fault means what? Once the fault appears, the fault will continue till that has been either rectified or replaced by another node. In contrary, intermittent fault is the fault that appears for a particular amount of time and disappears after that. And interestingly, we find out that this intermittent fault is following a distribution that is called a variable distribution. So in variable distribution, what happens? The appearance of the fault initially the appears or the appearance interval is longer initially. Later on, the appearance interval is getting shorter and shorter, and after some amount of time, the fault is becoming permanent. That we'll see. Now, another kind of fault is called as transient fault. Transient fault means it's a very peculiar kind of fault where the fault appears for a very less amount of time, maybe for microseconds, and it will disappear for a longer time, maybe years together. An example of your transient fault, I can say that if a node is working in the same time, if a big thunderstorm happens, so due to the thunderstorm, a very high magnitude noise is created and the sensor node behaves or sensor node misbehaves for that particular duration, which is very small due to the high magnitude of the noise, and later on it will do its job properly. This is one kind of transient fault, we can say, example. Similarly, some other kind of categorization may be your here hard fault and soft fault. Hard fault means it is the fault in the hardware. Maybe some of the blocks that we have talked about are not behaving properly. And soft fault means it is the computational fault. It may be your algorithm is misbehaving, your digital signal processing is misbehaving, or some of the intruder has hacked your system. That is called the node capture attack. These are some of the examples of your soft fault. And based on other criteria, these are the faults generally we can have. This may be crash fault, omission fault, timing fault, incorrect computation fault, train and stop fault, authenticated Byzantine fault, and Byzantine fault. These two are related to your security. So in this way, we can create a grid to see the interrelation between different kind of faults. So several techniques are present to find out the fault diagnosis. It can be broadly categorized into like your distributed approach and centralized approach. Centralized approaches are having its own bottlenecks. That's why we are not talking about centralized approach. So distributed approach, and distributed approach means every sensor node is having its own diagnostic protocols, and they can diagnose the network, which nodes are faulty and which nodes are not faulty. And based on that, different several techniques are there in the literature. So these are the techniques present. Those who want to go in details, they can download this paper that is available in IEEE. This is our presentation of it, that is the taxonomy. So what can be done? So these things we know that yes, the sensor nodes are faulty. Due to fault, we are having some life-threatening events may occur. So what we can do now? In the majority of the existing work, diagnostic messages are not sent as the output of the routine tasks of the network. So what happens? So it increases the message complexity or communication complexity. As I already cited, that if the communication complexity increases, then the battery power is getting drained very fast. So little work has been done on diagnosing intermittent and transient faults. So no work addresses the mechanism of determinate transient from intermittent fault. So which that is, as I told you, intermittent fault and transient fault are more or less similar. So our objective must be to discriminate between the intermediate and transient fault. And most of the work, they are just considering that nodes are static. They are not considering the nodes as dynamic, not moving. Mobility they are not putting. So these are the future research scope. Those who want to do the research in this area, they can proceed in this direction. So what can be contributed? An online diagnosis algorithm to diagnose hard and soft faults can be contributed. We can tune some detection parameters to intertest interval, and we can discriminate the transient from the intermittent fault, and we can diagnose the faults in dynamic environment. Sometimes it may be possible that while we are applying the test to detect a fault, at that particular time the node can behave properly, but after that the node misbehaves. Then it is our aim when to put the test message so that there will be a high probability that the node at that particular time is misbehaving. That is the challenge. So one of the example I can cite here, that is this is the last topic I will be discussing here. Intermittent fault diagnosis is very interesting. This is again you can see from here, that is the fault appearance duration and fault disappearance duration. So if we are putting our test message when the fault appears, then we can find out the fault. But if I am putting my test message during the fault disappearance, what conclusion my algorithm or my protocol will draw? That the node is fault free. But actually the node is faulty, which is coming under the category of intermittent fault. So judiciously and cleverly, I must put some number of test messages so that the test message and the FAD will coincide with high probability. So based on that, we have proposed a markup model. In that markup model, we can see that it is having a two-state markup model actually, where we are having a fault disappearance and fault appearance with some transition probability from fault disappearance to fault appearance with mu and lambda k. And once, as I told you, the intermittent fault after some duration of time, it will become permanent faulty. Once it is becoming permanent faulty, then if you replace it with the fault-free node, then it will continue like that. So based on this Markovian model, we have designed something. We have designed a Markovian model to detect the intermittent fault. So here we are putting some test messages and finding this the probability of fault appearance, and we are putting a condition here. This condition, based on this condition, you can see we have plot the diagrams. That is our objective is here to tune that P. You can see an intermittent fault originates from inside the system when software or hardware is faulty. By its nature, an intermittent fault will not occur consistently, which makes its diagnosis a probabilistic event over time. So the detection of intermittent fault requires repetitive testing at a discrete time, AT. So here the major thing is how to tune this T. the question arises, what should be the value of t so that with less amount of time my test message will coincide with fault appearance duration, and how many test messages I should send, because the complexity is playing a major role. Once I am sending a message means it is draining some amount of battery, so there must be some trade-off. So it is a kind of multi-objective optimization problem. So we have to address that trade-off by properly tuning this P. So if P is too large, then probability that the error appears after kth test and disappears after k plus 1 test, that increases, thus detection accuracy decreases. And diagnostic latency is expected to be more for larger value of t. Definitely, if the duration or the interval between two consecutive tests is more, then the diagnostic latency will be more. So the improvement in both detection accuracy and latency can be achieved with smaller value of t. However, the frequent exchange of sensor measurements will require. So these issues motivate to find out and trade off, as I told you, between detection accuracy and detection latency. So it's a multi-objective optimization issue now with certain constraints. So we can see that from this diagram, that is when T is getting tuned, so the number of tests required, and here also detection latency. You see that number of tests are decreasing as T increases, and detection latency increases as T increases. So it is having a conflicting objective. Now the two objectives are conflicting. So we can go for a multi-objective optimization with these objectives F1 and F2 with the constant function this one. So we have designed this to tune the detection parameter by using two different techniques, that is NSGA2 and 2LB MAPSO, and by using fuzzy we are finding the best trade. So this is the way we are using this. So this is all about the things that I need to discuss now. Thank you very much. If anybody got any question, then I will happy to address.
Audience, do you have any questions? As we all know that wireless sensor networks is emerging as the most dominant field in this era. We are really grateful to you, sir, for giving us this knowledge on different sensing models, multi-homing communication, and fault diagnosis, classification, and its some terminologies as well as its need. Thank you so much, sir.
Thank you very much.
My dear enthusiasts, let's talk about another great scholar, Dr. Ratnakar Das sir. Ratnakar sir is assistant professor in CSE department since 2011. He has passed BTech in 2002, MTech in 2005, and completed PhD from NIT Rourkela in 2012. He has published more than 50 papers in international journals of repute. Ratnakar sir's area of interest is machine learning, computer vision, image processing. He is doing research on domain of intelligent computing and computer vision. So I sincerely request Ratnakar sir to please share your ideas with our young minds. Sir?
Hello. So good.
Sir, Ratnakar sir, can we start now? My dear enthusiasts, let's talk about another great scholar, Dr. Ratnakar Das sir. Ratnakar sir is assistant professor in CSC department since 2011. He has passed his BTech in 2002 and MTech in 2005. He has completed his PhD from NIT Rourkela in 2012. He has published more than 50 papers in international journals of repute. Ratnakar's area of interest are machine learning, computer vision, and image processing. He is doing research on domain of intelligent computing and computer vision. So I sincerely request Ratnakar sir to please share your ideas with our students.
Sir, good morning, sir. Ramita madam here, sir. Sir, your voice is not audible, sir. Sir, Ratnakar, sir. Sir, can you hear me, sir? Hello, sir.
Hello, ma'am.
Yes, sir. Good morning, sir. Now it's audible, sir.
Now it's audible. Okay.
Yes,
So
yes.
thank you, madam, for this warm welcome.
Thank you, sir.
So, I thank all the organizers for giving me this opportunity to talk on this occasion. So let me share my slides. We'll have a discussion on the smart surveillance system using deep learning. So the slides are visible?
No, sir. It's not visible till now. Yes, sir. It's visible.
It's visible. Okay, fine. So let me, so there are a lot of network issues here. So let me just turn off my video so that there would not be any problem during the presentation. Okay.
Okay, okay, sir.
Okay.
Sir, kindly go for full screen, sir.
Now it's
Yes,
okay?
Yes, yes, sir. It's okay now. You
Okay.
can continue, sir. Thank you, sir.
Okay. So smart surveillance system using deep learning. So before going to the surveillance system, let us have some introduction to the deep learning, because this is one of the important concept nowadays. Many people and many companies are using this deep learning technique for their applications. So this deep learning is a part of machine learning. You can call this as a subset of machine learning. So let us start with about machine learning, then deep learning, then we'll see how this deep learning can be utilized for developing a smart surveillance system. Okay. So regarding machine learning, as we know that this machine learning is mostly deals with the data. When we have huge amount of data, we can build a machine learning model to take some decisions like human being. So this again, we can call this machine learning as a part of artificial intelligence, where this we try to mimic the human behavior or human intelligence into a machine, so that machine can take various decisions. Okay, so in the machine learning, it takes some data and we train a model on this data, and the trained model is used to make predictions on new data. Okay, so this is all about your data. So either it can be formulated in unsupervised way or supervised way, so that it can be trained and we can run an algorithm and execute an algorithm for deriving decisions, predicting some new values on a new data. Okay, so this machine learning, there are very well-known defined techniques in machine learning, that those things we can call as a shallow learning. When we talk about deep learning, so the counterpart is your shallow learning, where this SVM, linear regression, logistic regression, HMM, Gaussian mixture model, single layer MLP, we can call this learning as shallow learning, where the level of learning is a little bit low if you compare them to a deep learning scenario. Okay, so these have limited modeling capability of concepts and cannot make use of unlabeled data. So mostly these shallow learnings are derived for labeled data or for supervised problems. Okay. So now coming to the deep learning, so it's a kind of representation learning in which there are multiple levels of features, and these features are automatically discovered and they are composed together in the various levels to produce the output. As I've told this in this deep learning era, we try to use the data, huge amount of data, to make a model which learns faster, and the learning will be better than the conventional machine learning, where it has multiple levels of abstractions. So each abstraction layer tries to learn from the data, and which is passed on to the next layer. And by doing so for multiple times, we have a clear understanding of the data, and where we can understand the data from various sources, and we can take the decision in a better form than the conventional machine learning. So as I told, it's a class of machine learning which uses multiple layers of nonlinear processing unit for feature extraction and transformation. Okay, so but commonly it has become a buzzword for ANNs with more than one hidden layers. Now if you talk about deep learning, this is mostly based on the artificial neural network. Okay, so as we know, this artificial neural network with one or two layer can be termed as a shallow learning. When we go on increasing the number of layers, we can call that artificial neural network as a deep learning. Okay, however, there are differences. The deep learning models what we are using right now for different applications and the conventional neural network. Okay, so if you just see this artificial neural network, when the basic idea becomes, when we go on increasing the number of layers, so the learning will be more and more better, and we call that the deep learning. Okay. Now you can see here, this is a simple neural network where we have only one layer, input layer, output layer, with one hidden layer. Now if you compare that to a deep learning neural network which has multiple layers of hidden units. Okay, so if we increase the number of layers, so it is understood that the learning will be better. However, this format of deep learning neural network is not used in practice because of several limitations. Okay, you can see the complexity of the model. When you simply increase the number of layers without resetting the network, without having some modification, we are going to learn the things better. However, the cost of complexity, but complexity that means much more complexity. Okay. So here you can see that the basic difference between your machine learning and deep learning, where you can see that in the machine learning there is a extra step, that is feature extraction step, where we require a domain expert, where it tries to collect the unique representation or unique characteristic of the input object, which is fed to a classifier, and the classifier tries to decide whether the class of the object. For this case here, it is shown that it is a car or not a car. Now, if you compare that to a deep learning, there is no specific or specifically explicit step of feature extraction which has been embedded into in the classification phase. That means the deep learning models tries to extract the meaningful features or characteristics from the input object automatically, where no domain expertise is required. So this is one of the biggest advantage of deep learning models, where we do not have to worry about the feature extraction. It tries to derive the features automatically from the input data. Okay, so that it after extracting, it classifies the data like your conventional machine learning model. So mathematical proofs are also there, which shows that for some functions, shallow circuits require exponentially more circuit elements to compute than do deep circuits. As we have understood right now, if we increase more and more layers, as I told, the complexity may increase. However, but the recent deep learning models will have different types of connection and different properties, which says that we can mathematically prove that though we use a deep learning neural network, however, the complexity is much lesser than the with respect to its counterparts. Okay, so deep circuits can be intrinsically much powerful than shallow circuit. So now you can see this is a deep learning, deep neural network where the connections are used. All the neurons are connected to every other neuron in the subsequent layers. Okay, so these networks use the intermediate layers to build up multiple layers of abstraction. Now you can some data is fed in input layer. The input layer extracts some features. Those features are fed to the hidden layer. Again, they are non-linearly processed in the hidden layer. Output of hidden layer is fed to hidden layer 2. So by doing so, we go on collecting more and more abstract feature. In the final layer, they are combined and can represent the input object in a better way. So like, for example, if you are doing visual pattern recognition, so the neurons in the first layer might learn to recognize edges. So here, this visual pattern recognition, we concern about the images and videos. So if you input image or video, so what it can do, the first layer can learn edges. The second layer can recognize more complex shapes like triangles and rectangles, which requires these edges to be used for constructing the triangles or of their different shapes. Then another layer, the third layer, could recognize still more complex shapes and so on. Okay, so by doing so, you can just imagine that in each layer we try to extract some of the features which are combined and again fed into the next layer. So by repeating this operation multiple times, we will be able to represent a very complex shape in a better way. So these multiple layers of abstraction give deep networks an advantage to learn and solve more complex problems. Now, as we've seen that in the previous diagram of deep neural network, all connections are full. That means all the neurons of a particular layer is connected to every other neurons of a subsequent layer. However, the concept of this convolutional neural network came in 1995, which has a different concept than conventional ANN. So where the filtering operation, which is done in conventional neural network, is replaced by your convolution operation. So this in 1995, Likon has developed this concept, and they were able to reproduce good internal representation of the visual world. So this convolutional neural network has been used initially to represent the images and video to support recognition. So like again, this CNN can detect and classify objects into various categories, which is independent of your pose, scale, illumination, conformation, and occlusion and clutter. So there are various challenges that may have in the input objects, input images and videos. So this convolutional neural network is capable of handling or addressing those issues directly without having any extra effort. So previously we are using handcrafted feature extractor like in your cello learning case. Now we try to learn suitable representation directly from the images by use of this CNN concept. So this is the person who has developed this. Okay. So let us discuss some important points of CNN. Then we'll move on to the how these CNNs, RNNs will be suitable for developing smart surveillance model. So CNNs were neurobiologically motivated by the findings of locally sensitive and orientation sensitive nerve cells in the visual cortex. Okay, so this is, as I told, this concept of CNN has been taken from the similar concept of ANN, where we try to mimic the human behavior. Okay, and these are special kinds of multi-layer neural network, and it's again a feed-forward network that can extract topological properties from an input image. Like almost every other neural network, they are trained with a version of backpropagation algorithm. The similarity of these particular CNNs with ANN are they also use this backpropagation algorithm for like your artificial neural network, and they are designed to recognize visual patterns directly from pixel images with minimal pre-processing. Like it does the pre-processing, and it does directly automatically extract the feature without having any extra feature extraction step. Okay, like which is not available, which is not possible through conventional neural networks. So this is the structure of your conventional neural network. So which has various types of layer. Like here you have input layer followed by convolution layer. Convolution layer tries to achieve some of the features. Okay, followed by a nonlinear activation function known as rectified linear activation function here. Then followed by pooling. So again, this convolution plus ReLU pooling. These similar operations are repeated for a certain number of times. Then after getting extracting all the required features, they are finally combined in a fully connected layer. And if we are trying to classify a particular input object into various categories, we can use a softmax function at the last to in order to categorize the input object into its various categories. Okay. Now, apart from the classification, CNN also can be used for regression applications, where you may have to generate or may have to use a different network at the output layer, different layer function at the output layer in order to generate the regression parameters. Now, output of each convolved image is used as the input to the next layer. As I told, this each layer extracts some abstract features which are combined and fed the next layer. Here it says that output of each convolved image, like convolution operation, is used to extract as a filtering operation to extract unique characteristic or unique representation of the input image, then followed by pooling. Then that output of pooling is again convoluted and pooled and regenerates the feature and combined and then again process in the next layer. So by doing so, we will be able to collect the whole information from the input object in a very simple way rather than using the whole set of full connections. So these are the common layers in CNN: convolution layer, rectified linear unit layer, pooling layer, fully connected softmax. So convolution layer is basically responsible for extracting the meaningful information or features by using by a kind of filtering operation. Okay, so those who have understood the signal processing concept, they might have understood that how this convolution operation is useful in extracting input features from the input image or video. Now followed by a rectified linear, which is non-linear, which is a non-linear activation function, which transforms the input data to a non-linear shape, non-linear axis, where we can have a better representation of the input data of very high dimension. Now followed by ReLU layer, we have pooling layer, which is nothing but a subsampling layer. That means if the image size is this basically CNN is mostly uses a multi-resolution approach. Like we can extract features from the input object at multiple resolution. Let us suppose we have used the n cross n resolution at the first layer. In the subsequent layer, we may use at a lower resolution so that we can extract some more information from at a different resolution. So for achieving that, we as well as to reduce the dimension, we may use this pooling layer or subsampling layer, where the data, the size has been reduced to half, one third, one fourth, and so on. Then again that data is fed onto the next layer in order for filtering and activation. Then this after you filtering, ReLU and pooling operation, we can use a fully connected layer. So this fully connected layer is same as your conventional artificial neural network layers. Like first three layers, you can see the convolution, relevant pooling are not similar as your ANN. However, the fully connected layer and soft mesh layer are same as your concept that is used in ANN. Now coming to the video, so as we know, this video is a three-dimensional signal which has spatial coordinates as well as temporal coordinates. Spatial coordinates can be represented x, y with temporal coordinates as t. Like this video can be signal can be considered as an image if you see them at different times. Like video, we can, if you try to create a video, we can just combine different frames within a particular set of time, so that we can have a motion of the images at different instants of time, which the human eye sees as a video. That means video can be considered as a sequence of images. The challenge is how to model time t. So basically these CNN concepts have been developed for interpreting the images which are in two dimensions. That means only x and y dimensions should present. Now, when you talk about video, it has an extra dimension called temporal coordinate. So the challenge always lies in just interpreting the temporal dimension. Now, why this video analytics is critical? So this is very obvious. We know that there are applications of video analytics. Okay, so starting from robotics, developing robotics hands to do some variety of automatic tasks, to self-driving cars, where you can see that the cars can be moved on a road with other objects present without any driver sitting at position. Okay, so this also can be achieved by using the concept of video surveillance. Now this is another application where we can find different, we can use this video surveillance in sports activities in order to just recognize various activities. So this is a classification example where we try to classify the objects. You can see here we can classify the wheelchair basketball with a probability of 0.829, only basketball with 114. So you can see that wheelchair basketball has been identified as a particular. So these applications are possible by taking videos of input environment, videos of different environment, and analyzing them automatically through the use of these learning techniques. Now the basic classification between your image and video, you can see that we have in image data, we have only two dimensions, where the features are can be represented and can be played to a classifier like a normal classification task, where we can identify their semantic levels. Here you can see that human with 0.9 probability, not human with 0.1 probability. Okay, with level 2. Now the same thing can be achieved with video data with analyzing another dimension called the temporal dimension. You can see that same data with the extra dimension can also be identified, but however we need to represent the temporal dimension in a better way, so that we can, apart from the spatial dimension, we should also have access to the temporal dimension, from which some features could be extracted in order to fed to the classifier, in order to convert them, or in order to categorize them into different semantic levels. Now, before development of deep learning video classification techniques, I told that there are handcrafted versions of feature extraction, where we use histogram of oriented gradient, histogram of optical force. There are several other techniques are also here. I have mentioned only two. So we can use this handcrafted feature extraction technique. Then we can aggregate those features in order to classify a particular video. So let us not concentrate those techniques. Let us discuss how these convolutional neural networks or deep learning techniques can be exploited for video classification or video surveillance application, where we can say that these are very smart applications. I'll come to that in the in the proposed work. So here you can see there are various ways for classifying the video. First way is the frame level aggregation of 2D CNN, where we can aggregate the frame level information using pooling. where we initial. So these are the different evolution of research for handling this video, okay, or handling the time temporal information, because we know this 2D CNN is mostly popular for handling the spatial information from the input images. When we extend this 2D to 3D, so there are lots of developments made how to handle the temporal dimension. Now here in the first frame level aggregation, we lose the temporal information. Now in case of 2D, I think there are different techniques present here. Let us discuss from here. So you can see that image videos can be thought of a sequence of images where if you try to analyze the video using image format, we can use a simple 2D CNN like BGG, ResNet, Inception. There are different 2D CNN models, okay, where you can extract those features from the images. Finally, they can combine. That is feature aggregation or frame level aggregation. So when you combine frame level aggregation from different frames, it is like just we try to analyze the video. So from there we apply different pooling techniques, then concatenate them, and can finally classify these feature vectors using a classifier. Now, how to extract these frame level features? These frame level features can be extracted, as I told, from this variety of CNNs available. Like this is an example of here BGG16, which is a visual geometric group development by visual geometric group, which has 16 number of layers, and it uses different filters of different shapes. As I told, this CNN analyzes the input image at different resolution. So you can see here the input object of 224 has been analyzed at different resolutions. So finally, the lower resolution input image combined in a fully connected layer and finally classified. So this also contains the similar operations, the same operations called convolution, ReLU, pooling, finally fully connected and softmax. So in this way, you can extract meaningful features from the input images. However, you can see that there is a failure of analyzing the temporal segment, because we try to analyze the images in 2D. When there is a video, we apart from this 2D analysis, we also require a temporal analysis of the input image. So as I told this, we can do that by using frame level aggregation. So aggregation can be done at a variety of ways. We can analyze only single frame. We can have a late fusion, like we can analyze all the images, and finally at last we can fuse or aggregate all the features. Then we can have initially take multiple frames like in early fusion and try to extract the features. Now in case of slow fusion, we can use the different frame information at multiple instants. So there are a variety of ways in which we can aggregate the frame level features and try to analyze them. This is another way to aggregate the frame level, where it says that we have low resolution stream and your high resolution stream, where we can take a set of frames and we analyze them at low resolution, one structure, another structure tries to consider them in high resolution, finally they can be combined. So this is basically used by a variety of various researchers for analyzing the video in multiple ways. The summary says that these frame level pooling mechanisms provide a video descriptor which focuses on the salient instances in the video. Okay, the video descriptors for each videos are treated as a data sample or a classifier for classifying the video. However, these do not model temporal information, only relies on the salient frame level features. So here we have discussed that how these frame level or image level features can be combined in order to just get a representation of the video. However, this particular analysis, this theory is not true if you see that we are not able to analyze this temporal information properly. Only we are trying to aggregate the frame level features, where the frame level features can be combined in order to represent the video. Then how should the next question comes, then how should we model the temporal information? So in order to model temporal information, then another scenario could be you can have a 2D CNN in two streams. So one stream will try to analyze the spatial information, another stream could be used to analyze the motion information, because this video contains both spatial information and motion information. Here you see a particular image has been represented at different times. So where the motion information can be collected in a, you can see the blue arrow lines represent the optical flow information within different frames, 2 different frames at 2 instances, or you can take the 2 subsequent frames in order to compute the optical flow. Now, one stream could be used to analyze the spatial information like image. Another stream could be used to analyze the optical flow information. Okay, so here you see this motion single frame information can be used to compute the spatial characteristics. Another multi-frame optical flow, okay, which can be used in a temporal stream. That means we can combine this temporal information and along with the spatial information in order to do a score fusion of both classes. Okay, this is somewhat improvement of the aggregation of different frames. Now, what are the limitations? So the limitations are the appearance and motion stream are not aligned and lacking in modeling temporal evolution. You can see that here. So though we are able to take the spatial information and optical flow information, but they have to be aligned, which is not possible, which is very difficult in real time. While collecting the real-time video, if you try to analyze it online, you have to analyze the streams in a proper alignment. If your alignment is missing, that means those motion information doesn't correspond to the spatial image. That means your analysis will be completely wrong. So one of the major limitation of this particular 2D stream CNN technique is because of misalignment, which lacks in modeling the temporal evolution. Now comes the after that, people have thought of using this recurrent neural network, where this recurrent neural network is very much helpful for analyzing the time series data. So the concept of recurrent neural network is that means it works like traditional neural network, like where we try to collect the try to predict new information based on the past information. Okay, which cannot be handled by traditional neural network. Only uses the current information, and based on the current information, it tries to predict something new. Okay, however, in the recurrent neural network uses the past data as well as the current data in order to predict the new data. That means uses its past information. So it says the concept of the humans do not start their thinking from the scratch every second. So that means when you go on proceeding a particular topic, when you start from the topic, when you may not end the topic in a particular day, but when you start this topic on the next day, again you do not have to go to the beginning, because you have already obtained some knowledge. From there you start your reading. Okay, so that means in the similar way, this recurrent neural network uses the past data and as well as current data in order to predict the next instance. Okay, so traditional neural networks seems like a major shortcoming, where if, for example, if you want to classify what kind of event is happening every point in a movie, it is unclear that how traditional neural network could use its reasoning about previous events in the film to inform later ones. That means you can think of that in case of analyzing a movie, we need to have the concepts, need to know the events what has happened from the beginning, and those happens would be utilized for predicting the new events. So this is the concept. Here you can see here the neural network. There is a conventional neural network along with a recurrent connection. Okay, so this recurrent connections tries to address the temporal dependency modeling. Okay, so where it tries to collect the past information as well as previous information. So using both information, it outputs the value at time t. Okay, so it is thought of as a multiple copies of same network each passing message to a successor. So if you expand this particular block, you will get like this. Okay, here you can see that x0 is the current information which is passed to fed to a particular layer, and this information is passed along the next layer, and along with the present information x1. So you can see for computing a particular output, it uses two information from the one from the existing current information as well as the past output data, which can be mathematically explained like this. Here you can see h of t it can be described as the 10h, which is nothing but an activation function, WHS ht minus 1 and WHX xt. So just wait. Class Rock. So ht minus 1 is the output from the previous output, which is combined with the weight WHS, and the present information xt, which is combined with weight WHX. So both things are used and activated by a 10h activation function in order to generate the new output. So this seems like it uses the past information. That means some kind of temporal information can be preserved. So these RNNs are very much suitable for handling the time series data, and people have tried using this RNN for analyzing the temporal characteristics present in the video. Now there are a lot of shortcomings that have arisen in RNN. Though these RNNs are suitable for handling the time series data, but how long it can persist the data? So the measure of the past data means the time, because if you have a video of longer duration, RNN may fail to analyze the whole data. These RNNs are only suitable for analyzing very short time representation of the data. However, if you use videos of longer duration, RNNs are not suitable. That's why people have developed this LSTM, the long short-term memory concept. So in order to analyze the data of longer duration. Okay, so this is an improved version of your RNN. Okay, so it has two major characteristics, which is not possible for longer duration in RNN. So it does this using cell states. It has different cell states which can persist the information for a longer period. Okay. These are like conveyor belt that runs across time through which information flows. Then prioritizing information. So along with the persistence, it also prioritizes the information which has to be passed on to the next layer. That is also important. Like we have collected our past data for a long duration of time. However, if you see that in practical scenario, we may not require all the whole data, past data, to be processed. Okay, in order to represent or in order to just generate the new data. So it also prioritize the information from the past data. This means which deciding information is useful for future and which are useless, that can be erased. So using this characteristic persistence and prioritization, this LSTM has been very popular for handling the time series data. So it is this LSTM uses different gates similar to digital logic for controlling the time series data. So this is the picture of this short-term, long short-term memory LSTM. You can see that each individual unit uses 3 gates. The gates are known as cell state, forget gate, input gate, output gate. So these different modules in LSTM tries to achieve the persistence of the data, as well as prioritizing the data which has to be processed in the next layer. So using this LSTM and RNN concept, we can analyze the video and the temporal characteristic that is present in the video. You can see here this after learning LSTM or development of LSTM, people have tried to use the concept of CNN along with LSTM in order to derive the action class from video. So this LSTM tries to analyze the temporal information present, and CNN tries to analyze the spatial information. So both combined at different layers can be used to categorize or classify a video. So one of the major characteristics is LSTMs are sequential but cannot be parallelized. So this one of the limitations, or you can say one of the characteristics are they are sequential, they cannot be parallelized. So we need to deal the data sequential, means t-1 data is passed to t is passed to t+1, and along in this we cannot have a parallel analysis of the data. Now later comes the development of 3D convolutional neural network. So people have thought of like 2D can be used for analyzing the image frames or video frames. So why can't we go for 3D CNN, which uses three-dimensional convolution filters, unlike two-dimensional convolution filter in 2D CNN. So which can capture the data in multiple directions. Like we have 3 dimensions in video, so one dimension, 2 dimensions can capture the spatial information. Another dimension could be used to capture the temporal dimension in a video. So following that 2D architecture, we have BGG, Google Net. So those networks have been extended for in 3 dimensions. So this Google, Facebook has developed a architecture called C3D architecture. In 2015, Google team has developed I3D architecture. So these are the different versions of 3D convolutional neural network, which can extract spatial features as well as temporal features from the video in order to classify the video into multiple categories. Now this is the snapshot of your C3D architecture. You can see that there are different convolution layers. The concept remains same. However, the dimensions of the filters are different. So it contains 3x3 convolution kernels followed by 2x2 pooling at each layer. And the network architecture contains 8 convolution layer, 5 pooling layer, 2 fully connected. So this is the architecture developed by Facebook research for a particular video application. So it considers 16 frame clips to extract spatial temporal feature representation. Similarly, I3D architecture also developed by Google research, where 2D kernels has been replaced by 3D kernels, and there is also inflation operation done in the spatial domain. Okay, unlike C3D, it allows branching. Let us see how it does. So here you see there are 16 filters of convolution of 1x1 is fed to a bottleneck layer, which is passed to another convolution of 32 filters. That means the filtering operation is carried out in 3 dimensions. Okay. So then after your bottleneck block, there is an inception block, which is existing in I3D architecture. So unlike your normal 2D architecture, which has only one type of convolution, in this inception module, it have multiple shapes of convolution are achieved in a particular layer, so which are concatenated at the filter level and passed on to the next layer. You can see that 1x1, 3x3, 5x5 convolutions are combined with pooling layers. Then they are combined and passed on to the next layer. So this is the architecture of I3D, which is able to extract the meaningful features in the spatial direction, spatial version, as well as temporal version. So this is the whole network architecture of I3D. Okay. So we'll see that how this I3D and C3 network could be helpful for analyzing the videos. Though they are able to analyze the video in spatial direction as well as temporal direction, how the kernels are rigid. Like I told that in C3D or I3D architecture, the kernel size is fixed. Okay, so rigid spatiotemporal kernel limiting them to capture subtle motion. Subtle motion means if we have a action that we want to classify which occurs for a very few fraction of second, so those fraction of second are not able to achieve, not able to address by this spatiotemporal kernels, rigid spatiotemporal kernels, and no specific operation of discriminative feature representation also present. So because of this limitation of 3D CNN and other architectures, people have thought of deciding to develop new architecture, which is a combination of all these architectures for a video analysis. So here, let us discuss a case study on how we try to identify abnormal activities and classify them in an untrimmed surveillance video. So this is a very common scenario. Like we fix our surveillance cameras in different places. Now it is very tiresome to analyze them, the long hours of video by a particular person or a set of persons at a later time. So we want to do it automatically and make it smart, so whenever there is a abnormal action that happens in a particular environment, the camera should able to achieve that particular time or particular action, and also can categorize that which is that action is an abnormal action, it's a normal action. So based on that, some decisions of further processing or further operation can be taken out. Now here you see there are different frames for different examples of abnormal activities. So this has been taken from a database, crime data set. So you can see that there are abuse, arrest, arson, assault, burglary, explosion, fighting. So there are variety of abnormal activities are present in the scenario. So 13 types of activities have been chosen here. Now classification, we need to detect first whether the action is or activity is normal or abnormal. Then after detecting if it is abnormal, what kind of abnormality? Okay. So what are the challenges here? Challenges here: unavailability of large annotated data. That makes the problem is weakly supervised, and the sparsity of anomaly. This because abnormal activities happens very small amount of time. Okay, so that makes the problem sparse. Okay, and we have longer duration of video data, which has long range temporal dependency, which is can be modeled by LSTM, and the partial occlusion challenges always exist in image recognition. So this same thing also exists in video, and long and short anomaly activity. Okay, how to analyze all these or how to address all these challenges for video surveillance. So this is the example of partial occlusion. Here you can see two persons are moving, which has been occluded by. So if you want to analyze a particular action, if it is occluded, so it is not simple. Okay. So these are the scenario where different positioning on it under the skin or under camera field of view may get inadequate amount of light during evening and night time. So but our surveillance camera should be able to analyze these particular events at 24/7. That means at different illuminating conditions. So this is a framework for analyzing this weekly supervised learning for abnormal activity. Okay, so where we have a you can see this the training and testing phase, like your conventional learning approaches. You can see that the total video has been temporally segmented, and two bags have been created. One is your normal segment bag, another one is your anomaly plus normal. So why I call this as weekly supervised means it is very difficult to annotate all the videos. Okay, so we do have some of the videos which are already categorized in the data set, and other videos are not categorized. So this makes the problem weakly supervised. Okay. So from these two bags, we try to extract features which has an anomaly feature bag and normal feature bag, which is fed to a ranking model. So multiple instance ranking loss function has been used, MIL ranking loss function, which tries to generate a score for anomaly as well as normal. Okay, and try to just differentiate or maximize the difference of scores between anomaly and normal. So this is the framework. Once you try to minimize the multiple instance ranking loss function, we will be able to analyze a particular segment, whether this particular segment contains abnormal activity or not. So I'm not telling here that only a particular activity. We're just talking about a particular segment, whether this segment like 31 second to 41 second, if 10 minute segment, whether this segment contains the abnormal activity or not. So those can be analyzed. So after generating the ranking model, so we can use a thresholding function in order to analyze the activity as normal or abnormal. Okay, so this is the mathematical function for ranking loss. Okay, so we have you can see here that there are two constants have been added here. One is a temporal smoothing constant. Okay, because we require the data to be smooth in a temporal direction. Okay, we do not have because we try to analyze data for very slow motion also. Like if action has happened in a particular duration, very small duration of time, we should be also be able to analyze that. So that is achieved by the assuming this constant with the parameter lambda1. Another one constant has been added in the sparsity. Okay, because we know that motions are very sparse, actions are very sparse. We can also use a sparsity constant. So this makes a loss function. We try to optimize this loss function in order to categorize a video as a abnormal or a normal. So that is a detection part. In case of classification, only thing the difference is we can use a cross entropy loss function instead of a MIL loss ranking loss, and you can use this same classification model for generating the alumni class. Now this is our one of our proposition. Here you can see that. So this proposition contains similar framework where the we use a pre-trained I3D inception 3D model, which is a 3D CNN model. We can generate the data at different segments, and we do intra-clip and inter-clip pooling along TC and N directions in order to generate the feature. So the contribution lies here by applying different kinds of pooling and the different segments of the video. Okay, so after analyzing the getting the anomaly feature map, we fed this to a many-to-many LSTM model, so which tries to analyze the feature map in temporally. Okay, then finally we use the same anomaly score or same MIL linking loss function in order to generate the anomaly score. And we tried this MIL linking loss function basically tries to minimize the or maximize the distance between anomaly score and for maximize the distance between the score for anomaly feature as well as normal feature. Okay, so basically this proposition lies here basically for by proposing intra-clip and inter-clip pooling over different frames. So let us see. So in this framework, we have used this ImageNet and Kinetics dataset, where this, as we know, this I3D network tries to take 64 frame clips of resolution 224. We also use the same thing. So for intra-clip mission pooling, we use min-max, and inter-clip we use max pooling. So to obtain a single feature vector. So the contribution lies here in extracting the meaningful feature using this min-max and max pooling. So these are some of the results that we have obtained with different versions of the image with RGB, with RGB plus optical flow. Here we will only use RGB. So you can see that the one of the performance criteria, that is area under curve, going to be better with this proposed framework. This is another comparison of for our proposed scheme. Okay. Now let us have a qualitative analysis. Here you can see that. So this is a activity called abnormal activity called soft lifting. So you can see that there are ground truth versus prediction graph. You can see the scores generated for different frame numbers. You can see the green one is the ground truth and prediction. You can see that though this prediction, it has told that after frame number 750 some abnormality has occurred, but that is not true. Some abnormality has occurred after frame number 1000. So though it has some false positives, however, you can see that the abnormal activities are still be able to be detected by using this particular technique. This is for another one. So it says that abnormal activity continues for a longer period of time, which is not true. So though there are some values, but however we are able to detect that particular duration in which the abnormality has occurred. So apart from the quantitative analysis, so in this case we need to also have qualitative analysis. This is another for another scenario. You can see. So here we are able to match with somewhat with the ground truth. So these are the various references. Okay. So let me stop here. I will be happy to answer any questions if you have. Madam?
Yes, sir. Yes, sir.
Okay. I think I have covered in time, or?
Yes, sir. Yes, sir.
Okay.
Thank you, sir. I hope this will bring awareness in our students about neural networks and deep learning techniques. You explained us very well about different deep learning techniques like CNN, LSTM, etc. Audience, do you have any questions?
I think there is no question.
Any questions on deep learning concepts?
Sir, Ratnakar sir?
Yes, 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 ma'am.
Sir, I am having one question, sir. So,
Yes,
you know, sir, I'm working in image processing. My question is related to the pre-trained networks, sir.
yes,
So actually, I am now I am planning for the classification because some of the works I did in the segmentation. So
yes,
now I am planning for the classification when I gone through the pre-trained networks like RCNN and the YOLO V2, V4 like that. The pre-trained networks in
yes.
the file exchange, what I found they have taken the fast initialization. They have taken the .mat files, all the data sets. I found one example, they have taken person and car, and
Okay.
for that first what they are doing there in the file exchange, what I found in the example, so they are taking the .mat files, sir. So I am facing the problem in that point. Can you suggest me, sir, how to create that .mat files for that particular any data set, because
So
I saw many.
.NET, I think .NET files means they are MATLAB files. .NET files can be extracted, and we can create also .NET files in MATLAB very easily.
Yes, sir. Yes, sir. For any data I am creating, but for the complete data set, they
Yes,
have created the .mat file for the complete data set.
yes,
Like they have used the data set person and car.
yes.
For that data set classification, for the data set, they have taken the .mat file. And I am facing the problem there only how to create for the complete data set, how to create the .mat file so
You
that I
can
can
you
proceed
can
further.
have all the data in an Excel file and convert that into MAT file.
Okay, okay, sir. Then I will try because I
There
did
are there
some.
are functions available in MATLAB
Yes,
which will
sir.
help you to convert your MAT files into Excel as well from Excel to MAT file.
Okay, okay, sir. Then I will try. Sir, now one more questions, and I
Yes,
have gone through some papers also. So
yes,
I found some of the papers as we are calculating the accuracy, precision. These are the some performance measure parameters.
yes.
So some papers I found that global accuracy.
Okay.
And is there any difference in between the accuracy and the global accuracy?
No,
Because I am
no, no.
also
Global accuracy is nothing but suppose we have 5 classes. Okay.
okay,
So
sir.
we can compute the accuracy with respect to each class.
Hmm.
Okay. Or
Yes, sir.
a global accuracy. Global accuracy means overall accuracy.
Okay.
Okay. So that
Because
is the
they are
global
mentioning
accuracy.
global accuracy, and
No,
that's
no.
why
This is same as your overall accuracy or accuracy simply.
okay, okay.
Okay.
Okay, sir. Thank you, sir. Thank you so much. Thank you,
Okay.
sir.
Okay.
Thank you so much, sir, for clarifying our doubts. And you just helped us in getting knowledge about the deep learning techniques, which is really very important in this era. Thank you so much, sir.
Okay. Thank you,
Hello,
organizer.
hello,
Thank you,
sir. Just a
Subhajit
minute.
sir.
Sir, just a minute. Sir, one of our student having some doubt.
Yes, yes,
He
yes.
want to ask you, sir. He is
Yes, yes,
also
yes,
working in deep learning in image
yes,
processing. Yes,
yes,
sir.
yes,
Just I'm passing the mic, sir.
yes, yes.
Hello, sir. What is feed forward network? What is the role of feed forward network in CNN, sir?
So feed forward network means the features of a particular layer or data output from a particular layer and feed it to the next layer. Okay, it goes on doing that till you achieve your final feature. Okay, so when the output is again feedback to the previous layer, that we can call as a feedback network. Feed forward as well as feedback. Okay,
Okay,
so
sir.
feed forward means we forward our data to the next layer.
Okay, sir. Thank you, sir.
Thank you, sir. Well, audience, allow me to introduce another iconic personality, Dr. Prajit Kumar Biswal, sir. Professor Biswal, sir, is a great scholar with high experience in technical field. Biswal sir's teaching interests involve areas of VLSI design, VLSI architecture for signal processing, digital signal processing, advanced digital signal processing, digital image processing, digital electronics. His research areas are VLSI architecture for signal processing and image processing algorithms, biomedical signal and image processing. He has published over 9 research articles. He is a member of IEEE and MIE. So, sir, I request you to please motivate our young minds with your golden words.
Good afternoon. Am I audible?
Yes, sir.
Thank you. And thank you for the nice introduction. Anyway, it is around 12:25. The students are listening from the 10 a.m., I think 9 a.m. from the morning. So it is already 4 hours, going to be 4 hours. So I will not take much time. Is my screen visible? Is my screen visible?
No.
No.
No, sir. It's not. Yes, sir. Now you are presenting, sir.
Is it visible now?
Yes, sir. It is visible.
Okay. So if I got struck by anything due to any network issue, please inform me.
Yes, sir. It is also in the full screen mode. Yes, sir. Now you can continue, sir. Thank you, sir.
Okay, thank you. So from today morning, since we are discussing in the first talk, we have heard about very interesting talk regarding the packaging, and then we have listened about the communication, wireless network communication or sensor network communication. Then we have heard about image processing, including first one was regarding the image compression, and then we heard about the deep learning. So now I am going to talk about a technique. It is mainly a research area. My students have worked on it. So this is one area which is applied both in signal as well as image. So that is called singular spectrum analysis, SSA. So mainly I will discuss about this SSA based algorithm, which is applied both in biomedical signal processing as well as in hyperspectral image processing. Mainly I will not go deep into the mathematics part of this SSA algorithm, but I will mainly focus on how we have used this to achieve our goal, both in case of signal processing as well as in case of image processing. So first I will discuss briefly about the SSA. As I have already told, I will not go deep into the mathematics. And then I will tell how we have applied this SSA in signal processing, in biomedical signal processing. So mainly we have used this for muscle artifact removal. I will take a case study of this one, though we have used in other applications also, how the muscle artifacts in EEG signals can be removed using this SSA, or I will tell about we have modified a bit. We have made it adaptive SSA actually, so that we can efficiently remove the artifacts. We can predict and we can remove the artifacts, muscle artifacts from the EEG signals. So I will discuss about what is EEG signals briefly, so that people will have a brief idea about the EEG signals, then the artifacts, and then how to remove this muscle artifact. In the next part of the talk, I will talk about the 2D SSA, because in case of image processing, the single SSA, one-dimensional SSA will not be applicable. We have to use a 2D SSA. So 2D SSA has to be used for image processing. In hyperspectral image processing specifically, we will see how it is used, and briefly about the algorithm. And then here also we have used the superpixel concept. We have included the superpixel concept with the SSA and for the hyperspectral image classification. So coming with the SSA means already those the students who have studied the signal processing subject, they must be knowing about this, that in time series analysis, in any time series analysis, it can be stationary, it can be non-stationary. Now we can use single spectrum analysis, SSA, and mainly SSA is a non-parametric spectral estimation method. If you know, there are two methods of spectral estimation. One is parametric and another one is non-parametric spectral estimation. In case of parametric, mainly we talk about the probability density functions or cumulative distribution functions, mean, variance. These are the parameters that are used to estimate the frequency or to make the analysis. But in case of a non-parametric analysis, here mainly it doesn't require any parameters, or in some cases there is no distribution functions is also available. In some cases, distribution function is available without any parameter. In some cases, no distribution parameter is available. So that's why that is the case where we can use the singular spectrum analysis. Mainly, there are many decomposition techniques, as you must be knowing. Those who have studied some decomposition techniques, they must be knowing there are many decomposition techniques. Canonical correlation, CCA, there is EMD, empirical mode decomposition, there is EMD, ensembled empirical mode decomposition, there is VMD, variational mode decomposition, there are various types of variational mode decomposition, VMDs, which are mainly used to decompose the time series. Similarly, SSA is also used to decompose the time series into some sum of components, which from here we can the components we can interpret some data or we can interpret some information from that decomposition. Here, the singular spectrum analysis mainly relates to spectrum of eigenvalues of singular value decomposition. Those who have studied the mathematics, they must have studied about the eigenvectors. So mainly here it relates to the spectrum of the eigenvalues in a singular value decomposition of a covariance matrix. And mainly it is not in frequency domain representation. Though we are telling that it is singular spectrum analysis, it is not related to the frequency domain decomposition. It is done in case of in time domain only. Okay, so we are not converting. In case of VMD, mainly you can see we are representing in terms of frequency domain. But here in case of singular spectrum analysis, we are operating on same time domain only. So mainly the basic aim of SSA, what is the basic aim? To decompose the time series into sum of interpretable components, such as various periodic components, various noise components. So without any a priori assumptions about the parameter of these components. These are the steps, though as I have told, I am not going to the mathematics part. You have to first make a embedding. That means we have to create a trapezoidal matrix or Henkel matrix. Then we have to apply singular value decomposition. From the singular value decomposition, we will be getting the eigenvalue vectors. From the eigenvalue vectors, we will group it and we will make a diagonal averaging. So that we can decompose. After this diagonal averaging, we will decompose the signal, the series of signals into decomposition or decomposed components or sum of decomposed components. This is the basic about the SSA. Now, how we have applied this singular spectrum analysis in case of signal processing. As I have told you that we have used here in this particular case study, the singular spectrum analysis is used to remove the Mossel artifact from the EEG signal. So what is EEG signals? Many of us know this because many must have experienced also this one, the acquisition of the EEG signals. EEG signals, mainly it is a non-invasive portable technique. As you can see, this red part is the frontal part. So this is the frontal lobe, this is the back part. The green one is the back part. This is our the main part. You can take nervous systems. This is a representation only of the brain. So frontal lobe, as you can see, is responsible for problem solving, for emotional traits, for our speaking, for our voluntary motor activity. The frontal lobe are used. Similarly, this bottom part is the temporal lobe, which is mainly used for our memory, for our hearing, for our understanding any language or behavior. So this temporal lobe is responsible for that part. And then there is parietal lobe. Parietal lobe is knowing the right from left sensation. Actually, there is left parietal, there is right parietal. So mainly this lobe is knowing from the left to right and the sensations for reading purposes, for body orientation. This parietal lobe is responsible. Then there is occipital lobe, which is mainly responsible for vision and for color is perception. We can because if any problem occurs in this occipital lobe, we will not, our vision will be lost and we will not be able to recognize the various types of colors. So that's why this occipital lobe is responsible for that part. Then there is cerebellum, which is mainly maintain the body balance. So sometimes you will see you lose your body balance. So if there's some problem occurs in this cerebellum, then mainly this part is responsible. This part of the brain is responsible for body balance, coordination, and the motion control. All these are responsible by this cerebellum. And then the brain stem, the main nervous system, is responsible for breathing, body temperature, digestion, alertness, sleep, swallowing. All these parts are responsible, this brainstem is responsible for those functions. So this has been taken from one website, anatomyinfo.com. So what each does exactly? So as we have discussed here, it answers all the neuroscientific queries relating to the brains, to a response range of stimuli or conditions. Then it develops the brain development monitoring. If there is any sleep disorder, that we can know from the EEG. If there is any alertness, coma, brain death, all these can be monitored using the EEG. Then electroencephalography. EEG, if anybody is not knowing, so it is electroencephalography. So here also it is another major application of the EEG is the epilepsy, where epilepsy or seizure that is mainly used to detect, the EEG signal is used to detect the epilepsy. Mainly it is also used to detect at the early stage of the epilepsy. There are various stages of epilepsy, and this EEG signal is used to detect those epilepsies. Then for brain-computer interface, then for neuromarketing. Neuromarketing is one of the new concepts that is coming right now from the EEG study. They are getting the neuromarketing. That means what you are thinking in your brain. From that, the EEG signal will get the idea, and it will fed up the, like in Google, you must have seen that whatever you are browsing, next time it will pop up in your window. So the same thing here, what you are thinking, and that will come by from this studying this EEG signal. That is one of the interesting factor. And then how this EEG signal is accused, there are it can be 4 to 256 electrodes can be possible. A cap is where actually where various nodes are there, and nodes are placed at various points of the head or points of the brain, and then the data can be, the EEG signal can be accused. For medicals, either 10-20 systems where 21, 24, 32 or 64 electrode systems are used. Mainly maximum you will see in the medical sophisticated EEG signals are 128 electrode systems where they accuse signals from 128 points. As you can see, already we have discussed, this is the frontal node, frontal part, this is frontal central part, this is the central part, and then there is a parietal part, then this is the occipital part. So image signal, not the image, the signal can be, the EEG signal can be an acquisition from the parts, various parts of the brain, and we can get the data. So there are this characterization, you will see about the EEG signal. This amplitude is around 50 microvolts, frequency is from 0.1 to 100 hertz. I will discuss about that one also. The frequencies, there are various ranges of frequencies. Then another, how we characterize the duration of the electrical discharge, the latency, the location, the reactivity, the morphology. Morphology means shape of these EEG signals. From that we can study. So if you see the frequencies, as I have told you, it is from 0.1 hertz to 100 hertz. There are various brainwave types. Delta, theta, alpha. It is mainly classified into 5 types. That is delta, theta, alpha, beta, and gamma. And beta is again classified into low beta, mid-range beta, and high beta. And you can see the frequency range from 0.1 to 100 hertz. Delta is from 0.1 to 4 hertz. Theta is from 4 to 7.5. Alpha is from 8 to 13. Low beta is from 14 to 15, like this. It is gamma is from 30 to 100. And all these brain waves or all these frequencies have certain mental states. Like deep or dreamless sleep stage is nothing but the delta stage. And at that moment, the frequency of the EEG signal will be from 0.41 hertz to 0.1 hertz to 4 hertz. Like this, there are every alertness is the high beta stage, which is 21 hertz to 30 hertz. Then higher mental activity is gamma, that is 30 hertz to 100 hertz. So starting from deep dream to the dreamless sleep to the higher mental activity, the total EEG signals can be classified into various frequency ranges and various types of brain waves, starting from delta, theta, alpha, beta, and gamma. So there are artifacts means the problems that occurs when we are acquiring or acquisition of the, during the acquisition of the EEG signals. There can be non-physiological artifact, there can be physiological artifact. Non-physiological artifact means there is artifacts which may be due to the technology, like we are connecting the electrodes. The electrodes may be removed or may be disconnected due to some reasons. And due to the cable that is connected, there may be some artifacts may occur. In the artifacts means it's nothing but the error, nothing but the noise that occur in the original signal. Okay, there may be extensive causes like power line interference or baseline wandering, or if the person is moving, that is body movement, then also the artifact occurs in the EEG signal. Apart from this, there are some physiological aspects. So we are more concerned about the physiological aspect. So physiological artifact may be due to the ECG signal, may be due to the UOG signal, ECGs. Yes. So it may be due to the ECG signal, may be due to the EOG signal. ECG is electrocardiography signal, UOG is electrooculogram signal. It may be due to the muscles or EMG signals, electromyography signals. So there are various problems. One is ECG. The ocular problem may come due to the eye blink or lateral eye movement or eye fluttering. Muscles, that is may create artifacts, like if you're clenching the jaw while we are getting the data, or we are acquisition of the EG signal, or we are chewing something, or we are talking something, or we are swallowing something, that may also create some artifacts in the EG signals. So mainly here we will discuss about how to remove this muscle artifacts. Okay, so briefly description about what is the flat line artifact. Like you can see here, there is a portion here where the signal is not available. There is a flat line. So that is called flat line. There is also baseline wandering. That means the signal is not maintaining a constant baseline. So it is wandering about the baseline. Then there is movement artifact. The person moves during the acquisition of the signal, or then there is a artifact occurs here. Or there can be power line interference. Power line interference means some frequency interference occurs. So that can be removed using the notch frequency. Notch filters, where certain 50 Hertz filters can be removed. So 50 Hertz signal occurs in this. So how this is, because this is from 0.1 to 100 Hertz. So this may not be, sometimes it may not be recognized. So you have to find out those interferences and you have to remove it. Then there may be cases of abrupt slopes may occur due to the disconnection of the electrodes or pop-up of the nodes. These are the non-physiological artifacts. Coming to the physiological artifacts, as you can see here, ECG signals. This is the EEG signals, but there is a periodic ECG signals appears in this signal. So this is due to the electrocardiogram. We are acquisition EEG signals, but along with that EEG signals, ECG signal also appears, which has a frequency of 0.5 to 100 Hertz. So we have to remove those ECG signals, ECG artifacts. Similarly, ocular artifacts, like I have told you, there can be due to the blinking. The EEG signal may look like this. We have to remove. They're due to the lateral eye movement. Lateral eye movement means moving the eye from left side to right or right to left. That is the lateral eye movement. So during that also, it will create some artifact in the EEG signal. Then if there is a flutter, if you're fluttering repeatedly, then fluttering means blinking the eye repeatedly. Okay. So in that case also, we have some artifacts like you can see here. Now, in case of EMG artifacts, like there is jaw clenching, while the signal is acquisition, the EEG signal acquisition is being taken place. At that moment, it will clench our jaw. Okay, tightly it will clench our jaw. Then this type of artifacts will appear. Then there is a glossokinetic appearing in the EEG signal. If it starts chewing, then some artifacts will occur. So how to remove this? So mainly, if you can see, the EMG signal frequency is from 20 Hertz to 300 Hertz. So the signals which are beyond 100 Hertz, they are easy to remove. Okay, because the signal of EEG signal is 0.1 Hertz to 100 Hertz, as we know. So the signals beyond 100 Hertz can be easily removed. But the frequencies which are the signals or the artifacts which are within the 20 Hertz to 100 Hertz, how to remove those things? That is the main concern. So what are the challenges here? You can see both the EEG signals and artifacts both are non-stationary in nature, and they overlap each other's spectrum. As I've told you, they are in same frequency range, and they, in case of ECG also, they have similar spikes in like the EEG signals. So these are the cases, these are the challenges actually. You have to think about when we have to remove these cases. For bidirectional contaminating nature of OA, that means as I've told you, there is in case of ocular artifacts, the artifact occurs in both the bidirections, in positive direction as well as in case of negative directions. And because there is flutter movement, there is lateral eye movement which occurs because of both the directions. So how to remove those things? In morsel artifacts, like as I've told you, there is no proper reference channel is available. In morsel artifact, that is one of the important thing we have to first we faced, that there is no reference channel is available in case of EEG signal acquisition. And what is our aim? To use the minimization of instruments or minimum complexity, how to remove this, because in case of ambulatory services, mainly today's world, in ambulatory services we cannot fix each and everything in a single in an ambulance. So with minimum instrumentation, how to use this or how to remove this artifact, that is one of the important challenge in case of this artifact removal. So these are the notations that is used. One is contaminated EEG, EGC, EGT is the ground truth EEG, REMG is contaminating EMG, EGE, that is estimated EEG, EMGE is estimated EMG, and XR is parameter before artifact removal, and XE is parameter after artifact removal. So these are the notations that is used in this case. So now we'll go to the SSA based, because we have mainly focused on the SSA based algorithms. So SSA based morsel artifact removal, how this SSA is used to remove this morsel artifact. As you can see, there are various artifact suppression techniques that is available in the literature. There is CCA canonical component analysis, there is independent component analysis, there is EMD, there is EEMD, and there is CCA with MEMD. So various methods are used, and they are also used in case of multi-channel as well as single channel. We have mainly focused on single channel. As I have told you, we are focusing on lower computational complexity algorithm for ambulatory services. So in case of ambulatory services, there may be single channel EEG signals are available. So we have mostly focused on the single channel initial cases. Then we have focused on the multi-channel. So here if you see the characteristics of the morsel artifact, already I have told you it is from 20 Hz to 300 Hz and high amplitude variation. And non-stationary, it is non-stationary in nature. And the SNR range, the contamination SNRs can vary from 3 dB to 0.5 dB. So 0.5 dB noise means it is very high noise. Okay, so it ranges from 3 to 0.5 dB. So these are the characteristics of the morsel artifact. Now, how the singular spectrum analysis? Already I have told you, singular SSA, the mathematics part. Though I don't want to go into deep into. Already I have told the steps that is required in this case. So SSA is a time series approach which will decompose the original series into slow varying oscillator or noise components. So mainly it is two stages. One is decomposition stage, and another one is reconstruction stage. In case of decomposition, as I have told you, we applied only the trajectory matrix on the singular value decomposition or the SVD. Okay, so SSA will decompose this EEG time series signal, calculating the eigenvalue and eigenvector of the data. So trajectory matrix, if you see, this is the trajectory matrix. It consists of EEG signal and the morsel artifact. And the reconstruction of the artifact EEG signal from this trajectory matrix, it depends upon how we are able to eliminate this morsel artifacts from this. So this signal, what about the signal here we are taking? It consists of both the EEG signal as well as the morsel artifact or EMG signals. Okay, so here our main aim is from this trajectory matrix through this application of this SSA, how to remove this morsel artifacts. And here one of the factor we have considered, that is called the mobility. So how this mobility is calculated? Mobility is calculated using this formula, as you can see, square root of the ratio of the activity to the first derivative del square x by del square x dash root over. Okay, so this is the mobility. This mobility, as you can see, the mobility we have plotted here using the box plots. As you can see here, this is the EEG signal, mobility of the EEG signal. This is the mobility of the EMG signals. That means easily from the mobility we can differentiate the EEG and EMG. But if there are some noises, then how to differentiate? As you can see, this is 0.5 SNR, this is 1 SNR, this is 1.5 SNR, this is 2 SNR, this is 2.5 SNR, this is 3 SNR. So whenever it is having the noises along with that EMG signal also, then it mainly matches, as you can see, it is near or close to this EEG signals. So here, as here we have tried from this plot, actually we will know from which frequency range it as having. So mobility has been plotted initially to find out. So this mobility is used as a threshold, because we will find a threshold in this mobility, so that we can differentiate the EEG signal from the EMG signal, and we can remove those EMG signals. Okay. So here this is mainly the SSA routine. We will have the input contaminated EEG signal, then we'll do the decomposition. From the SSA decomposition, will get the eigenvalues, eigenvectors. Then we'll calculate the mobility of the eigenvectors. From this mobility, we'll remove the eigenvectors by thresholding the mobility. Okay, so here again one thing comes. So some work have been done already in this case where the fixed threshold is used. But fixed threshold is not a solution. Okay, because the contamination strength varies from one signal to another signal. So instead of that, what we have done, we have thought about a adaptive thresholding or adaptive SSA. That's why we are telling that this is an adaptive SSA. So once we have used the adaptive SSA, then we can remove this, half this mobility, calculate this threshold of this mobility, then using this reconstruction, SSA reconstruction again, because that is decomposition, then again using the reconstruction, we'll get the artifact-free EEG signal. Okay, so here this mainly two parts. One is training phase, another one is testing phase. So in the training phase, as you can see, one neural network regression is used for the adaptive purposes. So this SSA routine is used to, or this neural network regression is used to find out the updated mobility. So once this mobility is calculated, then from there we can get a threshold, and using that threshold we can remove the in the testing phase we can remove. Once you have that feature extraction using the threshold value, the mobility threshold value or the estimated threshold value mu th, then we can use to remove it in the testing phase. So here, why this neural network regression is used? There can be many methods. There many regression methods are available, but here we have used a neural network regression method, so that it requires less formal statistical training for this development, and they are also able to detect complex nonlinear relationship between the dependent and the independent variables, and all the possible interactions between the predictor variables can be detected using the neural network regression. So here we have used neural network regression to calculate the adaptives of the or to calculate the mobility threshold value. So some of the features that we have used in case of neural network regression, we have used Shannon entropy, we have used standard deviation, we have used activity, we have used activity of H dash, activity of X, activity of H dash, we have used mobility, we have used complexity. The mathematical formulas are available here. These are the parameters or features that we have used for the NNR. So this is the data set that we have taken. In the data set, we have taken two types of data set. One is synthetic data set and another some database that is available in the FusionNet. So one experimental data set that we have taken, and we have added the artifacts to it. We have taken the EEG signal and we have added the artifacts to it, and another simulated data set that is available already that we have simulated. These are the evaluation parameters: the relative root mean square, RRMC, there is correlation factor, peak SNR, and mutual information. Mutual information is mainly the statistical part of this evaluation. Then we have taken the, as you know, these are common factors: root mean square error, peak SNR, and the correlation factor. How the signal after removal, how it is more correlated or not. The true EEG signal and the estimated EEG signals, how they are correlated, that can be known from the correlation factor. If they are more close, then it is better removal of the artifact. And these are the results of this comparative results. As you can see, the with SNR 1.5 and this is SNR 0.5. As you can see, SNR 0.5 means very high noise is added to it. Still, we are able to recover this EEG signal, the EEG, true EEG and this estimated EEG. You can see that it is almost matching to this with some slightly artifact. But in case of SNR 1.5, it is able to exactly matches the true EEG with the estimated EEG is matching with the true EEG. These are the various parameters. Root mean square error. As you can see, the fixed threshold method is used. There is also EMDCC method that I have told you, that is for single channel. And this is the proposed adaptive SSA that we have used here. As you can see, that in this case, the root mean square error is very less. That is the more efficient. In case of correlation factor, it is almost matching. It is nearer to the 1 in case of our proposed method. In case of the PSNR also, it is a better PSNR compared to the other two methods. And in case of the mutual information, also this gives better result compared to the other two methods. As you can see here, the blue one is the SSA fixed threshold method, where some fixed threshold is taken to of the mobility to find out the SSA. Then the red one is EMDCCA, and the orange one is our proposed adaptive in all these cases. And you can see it gives better result compared to the other two methods. This is result of this contaminated. As you can see, one result already have shown with SNR 0.5, with SNR 1 dB, with SNR 3 dB, and this is also okay. This is 2 dB and 3 dB. Wrongly it is written. This is contaminated EG at 2 dB and contaminated EG at 3 dB. So as you can see, and the muscle artifact are removed using this particular adaptive SSC method. And this is the time of the execution. And this is not so important. Execution time, as you are increasing the segment, the time is increasing. And this is the result for the experimental data that we have taken from the data set. So as you can see here, the red one is the estimated EG, and the EG black one is the contaminated EG. As you can see here, this part, the contaminated EG part have been removed, and the line is straightened here in this case. Similarly, in case of the other point, there are many channels. So we have taken data from all the channels, and this is the real data that is available in the MIT BIH. And as you can see, the noises, wherever the noises are visible, this part mainly, and this part, the noises are removed using this particular method, using this SSA method. So here, what is the significance? Here we have used NNR along with SSA, and it is giving better result compared to the other methods that we have seen from the graphical outputs. Okay, then quickly we'll go through this 2D SSA because it is already approaching 1 o'clock. So 2D SSA based hyperspectral image processing. So here 2D SSA is used, and here another one, we have used a super pixels. Instead of using each pixel, in case of image, you know basic component is a pixel. But instead of taking each pixel and calculating the SSA, here what we have done, we have created a super pixel and or a homogeneous set of pixels using the super pixel method, and then we have used super pixel and SSA method. We have combined both and find out the feature. We have extracted the features from the because you know whenever we are going for the classification, first step is feature extraction, then is the classification. So here we have extracted the features using the 2D SSA along with the super pixels technique. So briefly about the hyperspectral. What is hyperspectral actually? This is the panchromatic image. You must be knowing there is only one band. And in case of multispectral, there are around 10 bands. As you can see, it is from 400 nanometer to 2500 nanometer. In that, the 10 bands of images are taken. But in case of hyperspectral, it is around hundreds of bands. In that same range, from 400 nanometer to 25 nanometer, we are taking hundreds of bands. So this is called the hyperspectral. The normal panchromatic image, there is only one band. Or in chromatic images, there are 3 bands, RGB or HSI or YAQ. There are 3 bands. But in case of multispectral, there are around tens of bands. In spectrum of hyperspectral, there are around hundreds of bands. So you see the information, the range of information that is available in case of hyperspectral, we have to deal with it. And this is one example of a Hyperion data cube. This Hyperion is a satellite by the this is an overhead satellite by the ISRO, by the NASA. This is not by ISRO. This is by the NASA, which has taken the Rishikesh and its surroundings. This is the image of Rishikesh, the various spectrums, the various bands that is available here. And here the important factor is the spectral specific signature. For a particular, as you can see, for this particular location, this is the spectrum for the vegetation. For the water, this is the spectral signature. For the soil, this is the spectral signature. This is mainly reflectance characteristics. Okay, so those who have studied image processing, they can better correlate with this. These are mainly reflectance factors, and for all the bands, this has been taken and the signature has been drawn. For the soil, for water, for vegetation, so you can see the signature is the spectral signature for each type of image will be different. So from the spectral signature itself, we can get the information or we can make the classification. These are the some of the simple data sets that we have used. Indian Pines data set that is available. This is the false color from image. This is the ground truth image, and these are the classes. The various colors are these are the various. So it is around 16 classes, as you can see. Alfalfa, various types of vegetations. Soybean, wheat, woods, buildings, stone, steel, towers. So it has various types of classifications. Then these are other experimental data sets that we have considered in case of HSI. We have considered Indian Pines data set. We have considered Pavia University data set. We have considered Botswana. We have considered Salinas, Houston 2018. Houston 2018 actually a computation data set, which has been given by the Houston University for a particular HSI related image processing related computations. And you can see this is the wavelength in which it works, and this is the size of the image that has been occurred. Okay, so mainly we have considered these type of images for these cases for the analysis of our algorithm. So this is the proposed algorithm. Quickly, I am telling this. So we have the input HSI, multi-level HSI, or multi-band hyperspectral images, and then we are using the segmented using the superpixel. We are using the superpixel segmentation, and in this we are getting the superpixel map, and from this superpixel map actually we are getting the 2D SSA, and from this 2D SSA we are reconstructing it, and then we are extracting the features. After decomposing, we are extracting the features. Then we are giving to a simple SVM classifier. Here we have not used any very high-end classifiers. Simple, we have used a simple SVM classifier, which is very popular to classify the hyperspectral classes. As you can see, the number of classes here, you will see number of classes in case of Indian Pines is 16. In case of Houston 2018, number of classes is 20. So 20 classes data. So number of classes are very high in these cases also, in case of HSI images also. So why the superpixel here we have used? Because to reduce the computational complexity, mainly we have used the superpixel. Then one of the very popular method, that is SLIC, you can search it, you can find it. That is simple linear iterative clustering method that mainly we have used because it used the k-means method, the simplest method. So SLIC used the k-means method to do the segmentation. There are mainly 4 steps. Already you know those who have worked on clustering, they must be knowing this one. So here we are taking a cluster center initialization, then we are doing the cluster assignment, then the cluster centers are updated with the mean value. So step 2 and 3 are actually iterative steps, and then finally we get the post processing, that is to enforce the connectivity by reassigning the disjoint pixels to the nearby superpixels. If some disjoint pixels are left out after this grouping or clustering, then we add them or enforce the connectivity by adding to the nearby superpixels. So once we get the superpixels, then we apply the 2D SSA on this HSI, and you can see after the decomposition, I'm not discussing about the 2D SSA here. This same steps, that is embedding, then the SBD, then eigenvector, then averaging. All these steps are offered, but it is in 2D method here. So here, as you can see, we have implemented the 2D SSA on the HSI scheme. This is the original one. A is the original one. B is only one component. C is 1 to 5 component, and D is 1 to 10 component. So if you notice C and D, there is no much differences. So instead of if you see only one component, that is little bit blurred. So instead of taking only one component or 1 to 10 component, we can take 1 to 5 component and do the processing. So by this decomposition, we are able to know how many components are required. So it differs from image to image, it differs. So from this, we can know how many groupings are possible, and accordingly, we will have the less number of data going for the feature extraction. Okay, so after applying this to DSSA on the superpixels, we decompose the data, and after that, we give it to the simple SVM classifier for the classification. So this is the effect of the training sample variations on the classification performance for the 4 type data sets, mainly Indian Pines data set, Pavia University data set, Salinas, and Houston 2018 data set. As you can see here, the SPSSA, the orange one, that is giving the better result in almost all the cases. You can see it here. The SPSSA, that is the orange one. We have used all other methods like SVM, EPF, SCMEK, R2MK, SGM, SSK, M Super PCA, 2D SSA, simple 2D SSA, and then 2D modified SSA, and this is the super pixel based SSA that we have proposed here. So this is the classification results of the Indian binds data set. All the methods have been specified here, and as you can see, the overall accuracy and the average accuracy is better in case of this SPSSA, that is around 98.15 and 97.5, as well as the statistical data, that is the kappa coefficient, in which is giving around 97.89. So in case of Indian pints, with only 3% training, we are able to get the better result in case of super pixel SSA algorithm. Similarly, this is of the classification map of the Indian pints, so it may not be that much interest. So last one is the SPSSA, which is almost giving similar value to the ground truth. Then there is also Pavia University dataset. As you can see, in case of Pavia University dataset, also we have got overall accuracy of 98.94 and average accuracy of 98.3 and kappa coefficient of 98.6. This is the classification map of the Pavia University database using the various methods. The last one, J, is the SPSSA, and that is used on the Pavia University dataset. Then there is Salinas dataset, where other methods are used, and in case of Salinas dataset, as you can see, we are able to achieve 99% overall accuracy and average accuracy. And this is the classification map. This is the classification of Houston 2008. This is a complex dataset actually with 20 classes. So here also you can see we are able to get overall accuracy of 83.57. It is not in the range of 90. It is in range of 83.57. And if we compare with others, it is giving better result compared to the other methods. And average accuracy also 79.95 and kappa coefficient of 78.73. And it is better compared to the other methods that we have used here. So this is the classification map of the Houston dataset. And also we have made the statistical analysis to get whether so we have performed the McNemar's test. So here the proposed method is the first one, like F1. It is comparison whenever we are going for statistical analysis. It is mainly between the two methods, F1 and F2. So here F1 is the proposed method, SPSSA, and the other one is the these methods that have been specified here. And as you can see, if it is more than 1.9, then it is a better one. So here almost it is all the cases we are getting more than 9. So here that means statistically also this SPSS methods give the better result compared to the other methods. So this is all about this. So we have told about the SSA method, how we have used this SSA for signal processing as well as image processing, and all the credit goes to first this is Professor Fabio Della Acqua. He is our collaborator. He is from University of Pavia, Italy, and rest of are my students, Dr. Chinmay Dora, Dr. Ramnanan Patra, and Subhasri Subodhi. So these three are my students, and mainly these works have been done by these students. So all the credit goes to them also for this work. So these are some of the references. Thank you. I hope I have completed in time. Already it is 1:10, going to be 1:10. I hope I have able to complete it in time. Thank you. If any question is there, you can take. Thank you for giving me the opportunity.
Thank you, sir. Thank you so much for explaining about the easy and data sets, classification of different data sets. On behalf, do you have any questions, audience?
Hello, sir.
Yes.
Sir, I'm Shishendu Rai, EC department. I have also worked on ECG signals. So, sir, have you worked on analog domain or sir digital domain, sir?
These are all in digital domain, digital
Yes,
signal processing.
Yes, sir. So, sir, I have also interest in the digital domain. So, sir, basically, sir, which software you have used, sir? Xilinx or?
No. This is we have not implemented this in hardware. This is simple MATLAB simulations. and we have taken digital signals or discrete signals as you can take, and we have implemented these algorithms. You can refer our papers.
Yes, sir. I will, sir, first implementing on MATLAB, then if it is
Then if
right,
you want to go for hardware implementation, then you can go for the Xilinx.
sir, which filter type you have used? Sir? Discrete wavelet transform or sir, any other filters?
No, here we have not used discrete wavelet transform. As I have told you, initially we haven't used discrete. Here for these two particular two cases, directly we have used the SSA on the signal itself.
Okay, okay. That means
For the decomposition, directly we have used SSA. DWT can be another options, but they are not giving so much efficient because there are other methods as we have compared. They are not giving better result compared to this SSA.
Yes, sir.
We have also tried with DWT.
The last question I am having, sir. Basically,
Yes.
sir, we are actually preferring the processing part in the digital domain.
Yes, yes, obviously, because the signal is in digital domain.
Yes.
The signal, whatever we are getting, that is digital signal
Yes, sir.
or discrete signal. You can tell that that is discrete signal.
Yes, sir. Yes, sir. So, sir, actually, sir, I had tried one implementation earlier on ECG filtering. There,
Yes,
sir,
yes.
I faced the problem about, sir, the noise, sir, the PSN, the RMSE value. So, sir, actually, which is better in terms of the? I mean, sir, have you used fixed point or sir floating point implementation, sir?
No, that's what I'm told. No, that whenever we are here, we have simulated only in MATLAB. If you go for the VLSI implementation or the digital implementation, the physical implementation of this, then you have to think about whether you are going for the fixed point or you are going to go to floating point. So generally, fixed point will give you the better result because with the fixed point, you can control the architecture better way.
Yes, sir.
Okay, because floating point, the architecture will be more complex. So it is better to go for the fixed point if you are going for the VLSI implementation.
Yes, sir. Because, sir, after 18 point, fixed point also becomes critical.
After certain points, so you have to check actually whether with the fixed point, because generally I think within 16 to 18 bits, you can achieve whatever the values that comes in case of EG or ECG signals. So 16 bits means whenever I'm telling total 16 bit means around 8 to 10 bits for the what part, real part, and the rest of the 5 bits for the fractional parts. I think that is sufficient for the fixed point implementation.
Okay, okay. Thank you, sir. Thank you, sir.
Okay.
Thank you, sir. The explanation you have given about the spectral estimation method SSA will surely help our students to develop and to do much more projects in future. If we want any help, we will surely contact you, sir. Thank you so much.
Thank you. Thank you.
On behalf of EC department, I really thank all the esteemed delegates, faculty, management team, and thank you so much for supporting us and organizing this, which can guide the youth, our students who are new upcoming scholars. Even though to each and every audience, I am really thankful for making this session a great success. Thank you all.
Hello. Sir, can we start the meeting now?
Yeah.
Yes, sir. Steve Jobs once said, "It's not faith in technology, it's faith in people." I
Your microphone is muted, I think.
Honorable dignitaries, distinguished delegates, respected teachers, and all enthusiastic students, a very good afternoon to one and all. It's a glorious moment to extend to you all a very warm welcome on behalf of the Department of Electronics and Communication Engineering, GIT University, Gunupur, who has clubbed us for the first edition of International Conference on Smart and Sustainable Technologies 2021. It's an opportune moment to refurbish and debate upon the problems of mutual interest with our esteemed guest. The conference schedules brushes upon a spectrum of exciting and benefiting themes that discuss the aspect of technology in development. Knowledge is wealth and technology is the comfort. This conference covers theory, design, and application of smart technologies and its application in different interdisciplinary fields. This will provide a forum for the researchers to discuss the key technological developments in their respective fields. The world is full of diamonds and gems, and we are having some of them here today to build this event. With all those words, I am extremely delighted to introduce Honorable Guest, Dr. Subhendu Roop. Good afternoon, sir.
Good afternoon.
Dr. Subhendu Roop is currently working as an associate professor in Department of Computer Science and Engineering, IIIT Bhubaneswar. He has obtained his MTech and PhD degree in Computer Science and Engineering from Jadavpur University and NIT Rourkela respectively. Professor Roop has more than 17 years of teaching experience. His research interest lies in the areas of image and video processing, computer vision, machine intelligence, video synoptics, medical imaging, virtual reality for historical heritage, human pose, and activity recognition. He has more than 50 research papers in reputed journal, conferences, and book chapters. He is the investigator of a sponsored project entitled ISCA2 funded by MEITY Government of India costing 63 lakhs. He is a technical consultant for IDCOL Software, Government of Odisha, Pinnacle System, and Robust Technologies. Currently, he has supervised 7 PhD scholars and 3 scholars are ongoing. More than 25 MTech students have already completed their dissertation under his guidance. He has developed 2 dedicated labs, namely Image and Video Processing Lab, funded by seed grant of IIIT Bhubaneswar, and Information Security Lab, funded by MEITY Government of India, where different PhD scholars, MTech and BTech students are working in the above mentioned areas. Apart from this, he was the head of Department of CSE from 2015 to 17. PhD program coordinator from 2014 to 2021. Currently, he is the professor in charge of training and placement at IIIT Bhubaneswar. With immense respect and honor, I warmly welcome Dr. Subhendu Roop to throw some light on the smart and sustainable technologies impending in future. Sir, please.
Okay, thank you very much for giving me the opportunity. And again, I repeatedly told, because GIT Gunupur is not a new institute for me. I have delivered so many technical talks in different departments like computer science, and I am a regular.
Sir, 1 minute, sir. Sir, your video is off, sir.
Okay, video is required because it will require some bandwidth. If it is essential, then I will on. Is it required? I will on my video.
No, sir, you can continue, sir. Thank
okay.
you, sir.
Okay.
in all my earlier talks, because as it is a technical talk in conference and time is too short, because within 45 minutes or 40 minutes I have to deliver. So in my previous talk, what I did, I have prepared the my presentation in terms of different areas, like already I have talked in video synopsis. It is a new technology, and I have also demonstrated different solutions what we have been provided to some agencies. Then earlier also I have talked with different surveillance problems, breast imaging system for a very full-faced computer-aided diagnosis systems, and our all contribution. Because though the earlier talk was a 2-hour talk or 1.5 hours of talk, it is possible for me to demonstrate all these things. So today talk, in what way I have been prepared. I request, my voice is audible to all of you? My voice is audible to all of you?
Yes, sir. Yes, sir, you are audible.
Yeah. So the today talk, in what way I have been prepared. So today I will be explaining a very emerging topic, because one of my primary area of research is computer vision and image and video processing, and I am also equally doing so many works in medical imaging. So one of the very emerging areas in medical imaging is the brain abnormality. So now it is a very commonly diagnosis disease among a varieties of peoples around the globe. So today presentation, in what way I have been presented. So today within 40 to 45 minutes, actually I will not interested to tell about our contribution, what we have been made so far, because it will take some time. So generally I will give you something about very generic idea, very brief idea about the particular topic, what this particular framework is basically suggested, what are the important modules of this particular framework. Then followed by, I will also highlighted some of the future improvement, in what way a particular researcher is going to start in this particular topic, maybe a PhD scholar or maybe an MTech scholars. Okay, so my today presentation, just a minute, I will share my screen. So my today presentation is basically dedicated on, my screen is visible to all of you? Is it visible properly?
Yes, sir. Yes, sir. It's visible, sir.
Okay. So the today talk is already I told earlier. So it will be very generic talk. I will give you a very basic background of this particular area. Then if someone is interested, I will give you some of the highlight or the focus to that particular area to go it more deeper to that particular field which we have been talking about. So today talk, the title of this talk is Development of Computer-Aided Diagnosis Framework for Brain Tumor Analysis. So our major objective is we have to develop some improved computer-aided diagnosis frameworks, which is basically commonly known as called CAD, because CAD is not only restricted to brain tumor analysis. You will develop any computational model for any specific disease analysis, whether it may be mammogram classification or breast cancer, or whether it may be brain tumor analysis, it may be liver abnormality, it may be your kidney abnormality, whatever it may be, what kind of disease we are dealing with. So this is the contents of this talk. The introduction to brain tumors. You have a clear idea what are the types of the brain tumor. Then what are the different type of brain imaging modality? Already you have heard about this term like MRI, CT scan, okay, functional MRI. There are so many. Then what is the role of a computer-aided diagnosis frameworks? Then already I have been pointed out there may be so many important or prime modules that affects the accuracy of that particular frameworks, which are segmentation, followed by feature analysis, followed by classifications, right? So now coming to the introduction to brain tumors. So there will be two broad categories of brain tumors. One is called benign and another one is called malignant. Okay. So first try to understand, suppose a particular mass or suppose a particular growth has already been incurred in your body. Every time you cannot make a conclusion that that particular mass or growth which has been occurred in your body, this is of cancerous in nature. That answer is not true. So benign means obviously there will be a mass, obviously there will be a tumor, but that tumor or that mass or that growth is not cancerous. That means it is not malignant or carcinoma. Whenever we are coming to malignant, obviously there will be a tumor, then that particular tumor or that particular growth is cancerous in nature. So if we have a very brief comparative analysis between these two, benign means low or zero rate of spreading. Suppose someone will go for a surgery, you have a growth in inside your body. So after a successful completion of the surgery, there is no chance of again growth of that particular tumor inside your body. It may so happen after surgery you will be completely cured. But whenever it will be a malignant, it may so happen a recurrent may occur after the surgery is also being done, or whatever may be the other treatment modality you are going to use, there may be a rapid rate of spreading. So if it is again found to be cancerous, then it is depends on the diagnosis or the doctor to make a conclusion that whether a particular patient will go for the chemotherapy or some other kind of treatment modality to cure that particular case. Okay, so this is the main differentiation between benign and malignant. One is not cancerous and another one is cancerous. Whenever we are coming to restricted to only brain tumor, one particular disease we are interested for this particular talk, then brain tumors may be of different types as per their structure is mainly concerns, because structure or shape. So one may be of a astrocytoma, means it is basically a glioma. These are some terminology, glioma of the, and a particular glioma is basically a star-shaped astrocyte cells. Because just like your breast cancer also, there may be different kind of cells, irregular, regular, there may be some circular, there may be some stellate shape, there may be some star shape. So based on the shape also you have to be identify what are the types. So astrocytoma is basically a glioma which is star shape, followed by glioblastoma multiforme, that is commonly known as GBM. This is most common and deadliest. So it is very, very means dangerous, that particular disease. Then there is also a pituitary adenoma. So it is basically occurs in pituitary gland. You have a pituitary gland in every human being. So possibly it is invasive in nature. Okay. Then meningioma is basically occurs on the meninges layers covering the brain and the spinal cords. Then also there is a medulloblastoma. Also it occurs in cerebellum of your corresponding brain. So again, there is a clear distinction is again whether you will go for what type of your brain abnormality or what type of brain cancer you are going to deal. Okay, but for the time being, for the very, very basic point, for a basic background, you have to know what are the different types of tumors is basically exist based on the different location we are talking of. These are a figurative description of this particular case, what I have been already told to you. Then as per the WHO, the grading of tumors is basically like that, because already you have been heard about this grade 1, whether your cancer is or whether it may be that tumor is grade 1 or grade 2 or grade 3 or grade 4. There are different grading system are there. So as per the level is concerned, there may be a low grade gliomas, there may be a high grade gliomas. As per the WHO grade is concerned, this low grade glioma is basically composed of grade 1 and grade 2. And as per the high grade glioma, they can be considered as grade 3 and grade 4. So these are the different characteristics. If it is grade 1, it may be benign. curable by surgery, what I earlier told, and higher survival period, maybe 15 years, 20 years, people may, or 25 years, till death also, it should not be any problem sometimes. And what kind of tumors? It is a pilocytic astrocytoma, means it is a type of cancerous, means what is the type of that particular glioma we are talking of. Whenever we are going to grade 2, it is slow growing. The growthness is very slow, not very rapid. It is slightly infiltrative. Okay, so the types are mainly, the tumor types are basically diffuse astrocytoma, pinocytoma, and these are some kind of types of the tumors which are basically belongs to grade 2. Whenever we are coming to high grade glioma, it is as per WHO recommendation, it is in grade 3. So basically in most of the cases it is malignant, cancerous, infiltrative again, but this kind of thing you cannot predict. The growth rate is very, very high as compared to the grade 1 and grade 2 what we are talking of, and grade 4 is mostly malignant, most dangerous, most deadly, highly invasive and aggressive growth. Within some months, if a proper treatment has not been done, you may undergo a severity of a particular patient. Okay, glioblastoma multiforme, pinoblastoma, these are some type of the tumor what we are talking of. So different types, different characteristics as per the grading. This is the grading of the tumor of a brain abnormality what we are talking of. Then coming to brain imaging modalities. So what kind of modality? There are different types of modality, but before we will go for MRI or CT scan or PETs, you have to know what is the general differentiation between this modality. So what is a neuroimaging modalities? Because this is, we are dealing with brain, means we are, our measure input is basically a neuroimage, what we have been obtained through MRI or PET scan